Hello students, welcome to the class. So today is our day 17 of this JEE 40 days crash course and we will continue with the electrochemistry chapter. So far we have studied about electrolysis and the Faraday's law of electrolysis. So we studied about two laws, right? First law and the second law. First law was related to the weight that would be deposited on your electrolysis process, and the second one was related to the equivalence if the same amount of electricity is supplied to through two different solutions. Okay, now in today's class our focus would be mainly on Nernst equation, right? So first of all we will try to define cell in a different way. So we've already seen one of the kind, which is electrolytic cell, but we will try to compare both of them. Okay, so our main focus will be first of all upon your Nernst equation, and second thing we will be discussing is the difference between electrolytic cell and your galvanic cell. So let us start our class. If you have a doubt regarding previous class, you can just post it here in the comment section. So this is our disclaimer. What are the topics that we are going to cover today? First of all, we'll start with the definition of cell and the types of cell. Next, we will look that what are electrodes. In a simple words, if I say, so electrodes are basically those strips of substances that can conduct electricity through it. Now, it can be both a metal or a non-metal. Then we will move on to salt bridge. So this is the second component of your cell. So first is your electrode and second is your salt bridge. Third, as I said earlier, we'll discuss the difference between electrolytic cell and your galvanic cell, electrochemical cell. After that, we will move on to representation of cell. So basically, the working of a cell is very complex. Now, to make it simpler or to use it in your calculations and all, we try to represent our cell in a simple fashion, and we will look upon the way how to represent it. Then after, we will move on to the importance of electrochemical series. So this is basically based upon the tendency of a given species to gain electrons. Lastly, we will move on to Nernst equation. So after covering all this part of a cell, we will see that how we will calculate the EMF of a cell. Okay. So first of all, let us start with what is cell. So cell is an arrangement of two electrodes which are fitted in the same electrolyte or in two different electrolytes. Means you can take two electrolytes, like in some example, if you see, the two electrodes are dipped into two different solutions. Okay, and in some of the cases you are dipping the two electrodes in the same solution. So if you are dipping in the same solution, of course the electrolyte will remain the same. If you are dipping into different solutions, then your electrolyte will change. Now in the case in which you are taking two different electrolyte, to complete the circuit we have a substance known as salt bridge. Okay, so salt bridge helps to complete the circuit. We will discuss about the salt bridge in detail in the upcoming slides. Now, what are the types of cells? As I said earlier, we have electrolytic cell. In electrolytic cell, we convert electrical energy into chemical energy. Okay, so how do we convert electrical energy into chemical energy? By providing external supply of current through a battery so that a non-spontaneous redox reaction can be carried out. Now, here is a diagram to represent the same. You can see here that we are applying EMF through a battery, and that battery is creating potential, and with the help of that, electron is flowing into the circuit, and through the solution the ions are carrying the current, and this is your completing your circuit. Okay, remember, electrons always flow through the wires. We have talked about metallic conduction and your electrolytic conduction. So in case of your wire, metallic conduction will be used and electron will be responsible for the supply of current. When we talk about the solution, in solution ions are responsible for the supply of current, right? And in this way, we are getting a electrolytic cell. So we have discussed about this electrolytic cell in the previous class also in detail. So I will not focus onto that, but to just distinguish both of them, we will see a glimpse of our electrolytic cell. Now the main part, which is our galvanic cell, also known as voltaic cell. So in these kind of cells, we convert chemical energy into electrical energy. And where is that chemical energy coming from? It is coming from a spontaneous redox reaction. Means the redox reactions which are carried out without any external factor. Okay, we just set up our electrodes in the proper electrolytic solution, and then the reaction goes on without any external application. And it in this way we use that chemical energy of that spontaneous redox reaction to get some electrical energy. And this is used in various fields of our day-to-day life. So take the example of your lithium ion battery you see in cars and all. So those are all based upon the same principle, which is conversion of chemical energy into electrical energy. Got it? Now can we take an example? Yes. So if you take zinc and copper, okay, you take a electrode of zinc and you take a electrode of copper, then you dip your zinc electrode into zinc salt solution. Similarly, you dip your copper electrode into copper salt solution. As soon as you do this, due to your electrode potential, you will see that current is flowing through the circuit if you connect your two electrodes through a closed wire. So here is the description of same. You can see here we have taken here a zinc electrode, and right side we have a copper electrode of brown color. Now what is happening? The electrons are being released by copper. They moved into the solution. Got it? And further, the species which take up the that electron, they become negatively charged, and further it is moved on through the salt bridge, and then it passes through the solution and moves to the electrode, and in this way the whole thing goes on continuously to produce electricity until and unless the concentrations are appropriate. We'll talk about that. Now, how is the electron flow? It is starting from left hand side and going on to right hand side, and this is a important convention you should remember. What is that convention? That always you keep the negative electrode on the left hand side, positive electrode on the right hand side. Got it? Now, this left hand side electrode is known as anode, this right hand side electrode is known as cathode. Now, what will be the direction of current? Remember, the flow of electron is always opposite to that of the flow of current. So, if your electron is flowing from left to right, the current will flow from right to left. Now, again, you can see that this is an example where your two electrodes are dipped in two different solutions, and to complete the circuit we have a salt bridge in between. We'll talk about how the salt bridge works in next coming slides. Any doubt till this point? Now next, moving on to the types of electrode. So there is something which is known as electrode potential. What is electrode potential? It is basically uh, the tendency of your species to accept electron. Okay. Now how do we know it? How do we calculate it? To do that, we used different types of electrode. The most common is your standard hydrogen electrode. So basically you take a standard hydrogen electrode and connect it to the species whose reduction potential you are interested in, and whatever current you get, you just note it down, and the potential that you get, you just note it down, and the potential is known as the standard electrode potential of that particular species. Okay, so hydrogen is taken as the reference part. Now how it is built? So this is a specific type of hydrogen electrode, and in this type of electrode we take hydrogen gas at 1 atm pressure, and in the solution part we keep hydrogen ion concentration as 1 m. So it is simply H plus concentration. Then after we use it as to define the standard electrode potential of different species. Now, what is the reaction? What is the half cell reaction that is going on? Basically, here your H plus is taking up the electron and it is going to H2. So this is your half cell reaction for your SHE. Now moving on to calomel electrode. So in some places you will also see the use of calomel electrode to define the reduction potential for various species. But remember, standard hydrogen electrode is the one which is used to calculate the standard electrode potential. This calomel electrode is something which is proper to some specific regions, okay, or you would say it is proper to some specific practical application and not everywhere. But you should know it because questions come from here. So it is also known as secondary reference electrode and it is used as needed, and it is based upon mercury chloride which known as calomel. Now how it works? So this is the half reaction. So basically we take mercury in the solution phase and we take chlorine gas, okay, and you take chloride ion in the solution. Now what is happening here? Your mercury is getting oxidized, and in that process it is releasing electron. Got it? So this is also used in some part to compare the standard reduction potential of different species, but in most of the cases and in your calculations also you will see that we always use standard hydrogen electrode. Again, how do we calculate standard reduction potential? We take our standard hydrogen electrode and connect it with the species whose standard reduction potential you are trying to calculate. And then after, whatever potential we get in the start of the reaction at standard condition, which is 1 atm pressure of your 1 atm pressure of your hydrogen gas and 1 molar concentration of hydrogen ion, at that particular time the starting EMF of your cell is your standard reduction potential of that particular species. We'll talk about that series also. What series do we get from this SHE? Next, as I said earlier, we will talk about now salt bridge. What is salt bridge? It is a U-shaped tube which is filled with a gel soaked in inert electrolytic solution such as ammonium nitrate. Now the important part is that why it is there? What is the need of that salt bridge? So this is very important part and you can see this in your redox chapter. Okay, we will not see particularly this thing in your electrochemistry, but you will notice this thing in the redox chapter in the NCERT. Now what are the characteristics of this ions which are present in your salt bridge? For example, NH4 plus or NO3 minus. First of all, it will never react with the ions. And if it is not reacting, means it will not get oxidized or it will not get reduced. So this is the reason we are taking an inert electrolytic solution, so that it cannot disturb the main reaction. Now, if it is not disturbing the main reaction, then what it is purpose? The purpose is to complete the electrical circuit. So whenever there is reduction at a particular place and oxidation at a particular place, there is accumulation of charge, right? So if I talk about anode, so on anode there is always oxidation. Now if oxidation is taking place, what must be happening there? The species must be releasing electron and positive ion must be released by the anode into the solution where your anode strip is dipped. Similarly, onto the cathode side, we are seeing reduction, and if reduction is occurring on that side, that means that negative charge is accumulated near the cathode. Now this extra charge which is being accumulated after oxidation and reduction, it stops the flow of current. Initially there is a flow of current, but it happens only for a small time. Now to make the current flow continuously, what we do, we introduce this salt bridge which has a inert electrolyte, and since it is an electrolyte, it will have a positive and a negative part. Now the accumulated charge on both sides are neutralized by the specific ions. Suppose if I say about anode, so I said that on the anode side we have accumulation of positive charge. So to neutralize that charge, your salt bridge will release this NO3 minus and it will go into the solution just to neutralize it, so that your current can flow continuously. Got it? Similarly, NH4 plus will go into the cathode part, and that will neutralize the negative ion. Is it clear to you? So what it is doing? It is just completing the electrical circuit. And how it is completing? By neutralizing the extra accumulation of charge. So this is written here. It maintains electrical neutrality in both compartments by allowing its ion to flow into the particular side. And of course it will happen. So what is driving that? Suppose there is an accumulation of positive charge. So positive charge always attracts negative charge, and that negative charge comes from your salt bridge. Similarly, your NO3 minus neutralizes your positive charge accumulation. So this is the role of your salt bridge, and it's very, very important. Got it? Okay. Now you can think it of in a different way also. Suppose you are taking a metallic conductor, which is wire, and you are completing your whole circuit with that wire. Got it? Now that must be a closed loop. Then and then only the current will flow. If you look upon upon a galvanic cell without a salt bridge, it will look like a open loop, not a closed loop, and therefore the current will not flow. It will only occur for a small time and it will stop. Got it? So in a way it is completing the circuit. And how it is completing, we discussed about the mechanism in detail, hopefully. Now, next, if I am clear about this electrolytic cell and your galvanic cell, then we can look upon its difference. First of all, as I said earlier, electrolytic cell is used to convert your electrical energy into chemical energy. And which type of chemical process is carried out using this chemical energy? A non-spontaneous redox reaction, okay, whose delta G is positive. So that reaction would be non-spontaneous in nature. Then if I talk about galvanic cell, then it takes up a spontaneous redox reaction and converts its electrical energy into chemical energy. Now for spontaneous redox reaction, delta G will be negative. Now I am trying to connect it with the thermodynamics, and it's very, very important. Questions are asked from the delta G parts, okay, in the exam of JEE and NEET both. Got it? Now, what is the charge? You should remember this. So we have a terminology, I would say, a mnemonic to remember it, which is known as lone. It is particularly for anode. So on left side, we have oxidation on anode, okay, and anode is negatively charged. So this mnemonic is particularly for your galvanic cell. In case of electrolytic cell, the charge is reversed. So now anode is having a positive charge and cathode is having a negative charge. Moving on further, the place of oxidation and reduction always remains same. So here oxidation will take place at anode and reduction will take place at cathode, and this is true for your galvanic cell also. Last difference is that ions are discharged at both the electrodes, okay, but in the case of galvanic cell, ions are discharged only at the cathode. Is it clear to all of you? Any doubt till this part? So let us move on further. Next is Daniell cell reaction. So Daniell cell is a special type of galvanic cell, and its reaction is given as Zn solid plus Cu2 plus, giving us Zn2 plus Cu. So this reaction is already known to you. We have seen this in the start of the lecture also. But the important part is that it is the first type of your galvanic cell, and it is known as Daniell cell. Now how do we represent it? So in the representation of a cell, first of all you should know that which species is undergoing oxidation, which is going reduction, and which species is oxidized as anode and which species is reduced as the cathode. So let's see it. If I look upon this reaction, here zinc is going to zinc 2 plus, means it is going from a neutral state to a positive state. Now how it is possible? It is only possible when it releases 2 electrons. Okay. So we can write the oxidation half reaction based on this idea. See, it is written here, Zn is going to Zn2 plus and it is releasing 2 electrons in that process. Similarly, if I talk about copper 2 plus, so it is going from copper 2 plus to copper. Here also, your copper 2 plus is attaining that same number of electron which was lost by the Zn, since this reaction is a balanced reaction. And what it is giving copper solid. Next thing, this oxidation is taking place at negative terminal and reduction is taking place at positive terminal, and we have seen this in the difference of your galvanic cell and electrolytic cell. Now, where is this oxidation taking place? As depicted by our mnemonic lone, it will take place at the left hand side, whereas the reduction will take place at the right hand side or the right compartment. Lastly, what is the process here? So we are going from Zn to Zn2 plus. So you represent it in this way: Zn solid, then slash Zn2 plus aqueous. Now what is this slash here for? This slash that is present here, it is denoting that there is a phase difference between these two. One is in solid phase, other one is in the aqueous phase. You can see the same slash here in the Cu2 plus Cu. Okay. Here also the copper 2 plus ion are in the aqueous phase and copper solid is in the solid phase. So to differentiate between these two phases, we have a oblique sign or a slash sign here. Now, if this is clear to you, let us write the complete cell representation. As I said earlier, first you have to verify that which is undergoing oxidation, and that is obviously our zinc to zinc 2 plus. So we will write as it is zinc solid to zinc 2 plus and we'll put a phase boundary here. Then after, we will write the reduction part and we will also introduce the cell phase boundary here also. Now, next important thing is your double line. You can see two lines here in the middle. These two lines are representing that we are having these two reactions in two different compartments and they are internally connected by a salt bridge. Okay, so there is meaning to each and every notation that you are seeing here. Now, where is electron flowing from? It is flowing from the zinc and going on to the copper 2 plus. Means the electron released by zinc is going to the copper 2 plus to make it copper. So that is the reason we are writing the oxidation on the left hand side and reduction on the right hand side, because this is the way your electron is flowing. So let us just go through each and every notation. First of all, oxidation is taking place at the left hand side. So we are writing the oxidation part on the left hand side and there is a phase boundary between the two components of this oxidation. Similarly, on the right hand side, we have two components and there is a phase boundary to differentiate between the solid and aqueous phase. Then this way of writing oxidation at left hand side and reduction at right hand side shows that electron is flowing from left to right. Lastly, we have a line here. So two lines are present here. So these two lines are representing that your two solutions are in, or your oxidation or reduction reactions are occurring in two different solutions and they are internally connected by a salt bridge. Any doubt in this part? So this is the most important part, I would say, regarding this whole chapter of Nernst equation or whole part of Nernst equation, because in most of the questions you will see that rather than writing the whole situation in terms of word, you will be given with a cell representation in your question, so that you can collect all information from this cell representation and then solve the numerical for particular value. It can be for EMF or it can be for Gibbs free energy or any other parameter. So this should be clear to you. Any doubt in this part? Anyone who has a doubt in this case? You can just post your doubt in the comment section. So after this, we will do questions on the same. Okay. Now we will see questions on electrolysis also, because that is something which is, I think, more important than your Nernst equation, because questions are asked from that part in most of the papers. But still, since two parts are there and they are equally important, I would say. But electrolysis part is much more important, and we will do questions on that part also today, and we will do questions on this part also. Is it clear to all of you? Any doubt in this part? If it is clear to all of you, now we will move on to the next thing, which is electrochemical series. As I said earlier, so we tried to calculate the standard electrode potential for each and every species which are important for our industrial purpose using the SHE, standard hydrogen electrode, and on the basis of that we constructed a electrochemical series. Now what is that series? Let me introduce you to that series. So it is arrangement of metals in the order of their decreasing tendency to lose electrons. Got it? And it is based upon the reduction potential, the standard reduction potential at 25 degrees Celsius. So this is your table. Now just look upon hydrogen. Since we are taking hydrogen as your reference part, therefore the standard reduction potential for hydrogen is taken as 0. Okay? Whereas if you look upon the upside, you have negative potential, means these species have a less tendency to get reduced. Okay? Similarly, if you look after hydrogen, you can see positive value of reduction potential, meaning that the species which are present after hydrogen have a greater tendency to accept electrons. So as you move from top to bottom, there is an increasing tendency for reduction. And since there is an increasing tendency for reduction, so the most powerful oxidizing agent will be this F2, because it has the highest reduction potential, so it will easily get reduced and oxidize the corresponding part. Is it clear to you? So this series is telling us 4 important points. What are those 4 important points? First point is that your F2 has the highest reduction potential and it is the strongest oxidizing agent. Okay, first 2 points regarding the fluorine. Then if I look upon the upper part of this table, then we can say that lithium has the lowest reduction potential. If it has the lowest reduction potential, then the oxidation potential will be, of course, highest, because it is just the opposite tendency. If it is lower in one, then it will be higher in the other. So lithium will have the highest oxidation potential, so it will be oxidized easily. As a result of this, it will be a strong reducing agent. So again, I am repeating all of this. Fluorine is the strongest oxidizing agent and has the highest reduction potential, whereas lithium is the strongest reducing agent and has the highest oxidation potential. Now one more question to all of you. Can you tell me what will be the oxidation potential for lithium if the reduction potential for lithium is minus 3.05? So to answer this question, there is a very simple way to do so. If you know the oxidation potential or the reduction potential, you can calculate the other part very easily. There is no need to have the other part. Okay, you can easily calculate it from the single value. And what is the way? So if minus 3.05 is the reduction potential of lithium, then plus 3.05 is the oxidation potential for lithium. As simple as that. You just have to convert the sign and you will get the corresponding part. Similarly, if I ask you, can you tell me the oxidation potential for fluorine? Then what you will say? You will say that the oxidation potential for fluorine is minus 2.87. Any doubt in this part? So reduction potential of any species is equals to the negative of the oxidation potential. You have just have to switch the signs and you will get the other corresponding part of the same species. And this is something which is very important in your numerical calculations. Okay. Now, with all of these known to you, we can move on to Nernst equation. So this is basically the highest potential of a given cell, which is known as EMF, and it is creates a relationship. This Nernst equation creates a relationship between electrode potential and the concentration of the solution. So if you know the concentration of your electrolytic solution, with the help of that you can know the EMF of that particular cell. How do we calculate it? It's very simple. The general form of this equation is E cell is equals to E naught cell minus 2.303 RT by NF log Q. What is this Q? So this Q is your reaction quotient. Therefore, if you know the standard EMF of that particular cell, you can calculate the EMF of that particular cell at any other condition. Okay, so standard condition should be known to you, and with the help of that you can calculate it for any other condition. Now what is standard condition? Where the concentration is unity and the temperature is 25 degrees Celsius. So that is something which is known as standard condition. And if you know it for standard condition, you can calculate it for any other concentration where it is not equals to unity, means the molar concentration is not 1 m. Now let me tell you the different parts of that equation, which is very important to solve numericals. The first part is n, which is the total number of electrons lost or gained by the process during your redox reaction. Next is F. You all of you know about this F. It is the 96500 coulomb, which is equals to your charge due to 1 mole of electron. Okay, also known as Faraday's constant. Now this is an approximate value. It is something which is 96485, but we write it approximately equals to 96500 in your calculations. If the value is mentioned in your question apart from this value, any other value, then you will use that value. But if it is not mentioned, you can obviously use this 96500 coulomb as your F value. Further, T is the temperature. If you want, you can take it as 298 Kelvin, which is your standard condition, and R is your gas constant, and in terms of SI unit you will write it as 8.314 joule per Kelvin per mole. Now what is this Q? I said it earlier, it is your reaction quotient. If you go back to your redox reaction, then you can clearly say that concentration of your electrode will be always unity. So concentration is much more needed in case of liquid solution or your aqueous solution that your electrode is dipped in, right? Because solid will always have a concentration of unity, and we have seen it. Therefore, your quotient become equals to oxidizing species versus reducing species, because on the product side we have the oxidized species. Just go back to your redox reaction and you will clearly see that the oxidized species is on the right hand side, and since it is present on the right hand side or on the product side, we will write it in the numerator, and the reducing species will be in the denominator. Next, if I write this particularly for equilibrium condition at 298 Kelvin, then first of all for 298 Kelvin it will be equals to E cell is equals to E naught cell minus 0.059 by 91 by log Q. So we put this value of R as 8.314, T as 298 Kelvin, and F as 96500. Now remember this equation, this is something which is operating equation. Until and unless your temperature is not changed from 25 degrees Celsius, you can easily take this equation where the value is already put 10. Okay, put, and further you can calculate the E cell. Next, the EMF of a standard cell does not change with temperature, because EMF is defined at a particular temperature which is 25 degrees Celsius, and it will remain same. So the E naught cell value will always be the same for a given electrochemical cell, or which is your galvanic cell. Got it? Is it clear to all of you? So this equation is very important. Now further what you can do, you can just take Q equals to K and try to find the equation that you will get after putting Q equals to K. So what will happen in that case? So let me just write the new equation. So if we take the equilibrium condition, then at that condition your E cell becomes 0. So this is very important for you. When your reaction quotient Q becomes equals to K. So that will happen at equilibrium. At that condition, your E cell will be 0. Now, your Nernst equation can be written as E naught cell is equals to 0.0591 by n log K. So this is just the simplified form of your Nernst equation at 25 degrees Celsius and at equilibrium condition. So you take E cell equals to 0 at equilibrium condition, and for temperature 298 Kelvin, your constant becomes 0.059 by n, and your Q become equals to K. So this is something which is very important in your calculations, and questions are asked from here to calculate the equilibrium constant. Here what we have, K is the equilibrium constant and n is the number of electrons involved. Then next important aspect is your thermodynamic aspect. What do I mean by this? In the start of this chapter, I said that, or of this discussion, I said that we are in search of spontaneous redox reaction for galvanic cell. Now, how do we decide that a given reaction is spontaneous or not? So, the easiest way to do so is your calculation of your standard Gibbs free energy. Okay, so if the standard Gibbs free energy for a given reaction is equals to negative, then in that case your reaction is spontaneous. Suppose, how do we calculate it? What is the formula for that? So it is delta G naught is equals to minus NFE naught. Okay, where delta G naught is the standard Gibbs free energy. You can just push the equation further, and rather than writing it as delta G naught, you can start from delta G is equals to delta G naught plus RT ln Q, and from there you can get your Nernst equation also. So you can try this by yourself. It's very easy to do so. Now for the time being, you should remember this equation. If it is not defined for standard condition, then in that case you will simply write it as delta G is equals to minus NFE cell. If it is for standard condition, then it is delta G naught is equals to minus NFE naught cell. Any doubt in this part or the Nernst equation? Anyone who has a doubt in this? Okay, so now we will switch on to questions. So this was all for the theory part. So this is your first question, and it is from Faraday's law of electrolysis. Okay, question is saying that you are supplying a current of 2 ampere and it is supplied for 5 hours through a molten tin. Then the amount of tin which is deposited on the right hand side is 22.2 grams. Next, you have to calculate the oxidation state of tin in salt. You are given with the atomic weight of tin, which is 118.69 grams. So, how do we calculate it? To calculate the oxidation state, you have to calculate the charge on the tin ion. Okay, and that is nothing but your n factor. So basically you have to calculate your n factor, and it can come directly from your first equation of first law of electrolysis, which is W is equals to ZIT. Okay. So weight is already given here. It is 22.2 grams. Z can be calculated. Further, I is given here, which is 2 ampere, and time is given in hours. So you have to convert this hours into seconds for SI unit. Okay. First, you will calculate Z. Okay. Then from Z, you can easily calculate your part, which is your N factor, because atomic weight is already known to you. Got it? So what is the way to calculate your Z? It is equivalent weight by 96500. So Z is simply your electrochemical equivalence. So if you first calculate Z, from there you will get your equivalent weight, because Z is equals to equivalent weight by 96500. Once you got equivalent weight, then further equivalent weight is equals to atomic weight by N factor. So equivalent weight can be used to calculate the N factor, because N factor will be equals to atomic weight by equivalent weight. Got it? Is it clear to you? It's very simple. Just go step by step and try to calculate this. So I am giving you some time to solve it. If you just calculate it by yourself and give your answers in the comment section. So 4 options are given here: A, B, C and D. So there are only 2 options which are possible, which is +2 and +4, obviously, because tin can show these 2 oxidation states only in most of the cases. But still you need to calculate it. So what do we do? First we calculate the Z. Then from Z we calculate the equivalent weight, and from equivalent weight we calculate the N factor, which is your valency. So what will be the answer for this case? Remember, to convert your hours to second, you have to multiply it with 3600. Anyone who got the answer for this question? Just write your answers in the comment section. What will be the answer for this question? Anyone? Just comment your answer in the comment section. You have to calculate the N factor here, which is your oxidation state of tin. First calculate the Z, then from Z you calculate your what? Your equivalent weight, and from equivalent weight you can get your N factor. Anyone who got the answer? So I've created a poll in the comment section. You can just poll it there if you want. Okay, so right now I'm moving on to the answer. If you want, you can just poll it there. So what will be the correct answer? The correct answer will be +2 oxidation state. Now I will use the formula directly to solve it. How? So for equivalence of tin, we have this formula, which is weight of tin by equivalent weight is equals to I into T by 96500. So we have simplified this thing. Okay. So rather than writing it as Z, we are taking directly the equation. So Z will be equals to what? Equivalent weight by 96500. So we have cross multiplied it here. Okay, as simple as that. There is no rocket science here. Now we'll put the values. So weight of tin is given as 22.2 grams. Okay. Then further, the value of current is 2 ampere. Time will be 5 times 60 into 60, because 5 hours means the units are in not in SI. So you have to convert it into SI units by multiplying it with 3600 or 60 into 60. Then divided by 96500. Next, If you solve it for equivalent weight, you will get it as 59.5. Okay. Now what we will do? We will use this equivalent weight to calculate the valency of tin. So equivalent weight is equals to atomic weight by n factor. Therefore, your n factor or valency of tin is equals to atomic weight by equivalent weight. So atomic weight is already given, it is 118.69, and divide this thing by the equivalent weight. You will get it as 2 approximately. Okay, so if you are getting a decimal value, just round that figure to a closest integer. Therefore, we can clearly say that your tin is present in +2 oxidation state, and hence option A is correct. Any doubt in this part? Is it clear to all of you? So I have just rearranged this equation so that we can directly calculate the equivalent weight rather than calculating it in multiple steps. Because weight of tin is equals to Z into I into T. So in place of Z, I have written it as equivalent weight by 96500. Any doubt in this part? Anyone who has a doubt, they can ask it now. Okay. So I am assuming that it is clear to all of you. Moving on to the next question. So you are given a sample of copper which is having zinc impurity inside it, and you have to purify this by electrolysis. So basically, you have to take out the pure copper out of this zinc copper mixture. Now you have to decide that what is the appropriate electrode. So you have two samples, right? During electrolysis, you take two samples. One is the pure form, the other one is the impure form. You have to decide that in which electrode you will take the pure form and in which electrode you will take the impure form. Now question arises, how you will think about it? Very simple, just go back to your basics of your electrolysis. In electrolysis, where is the reduction occurring? Or you can say, where is the pure zinc obtained? So it is occurring on the cathode side. Okay. Your cathode is the place where your reduction is occurring. Got it? Therefore, you will keep your pure zinc on the cathode. Any doubt in this? What did I say? I said that in the case of electrolysis, we take the species as cathode which is going to be oxidized. And for electrolysis, the oxidized, not reduced. Okay, the species which is going to be reduced. Or we can say that the place where your pure thing will be obtained, or your pure metal will be obtained. So that part is clearly your cathode. And hence, we have now two options left, A and D. A and D both have pure copper. Next, we are given with the two samples. It is very obvious, if at one place we are taking pure copper, pure zinc, at the other part we will take the impure sample. Now from that logic, it is very clear that your correct answer is option number D. So what will be the correct answer? Option number D, that is pure copper is taken at cathode and impure sample is taken at anode. Next, how did we think about it? So just think about electrolysis process. At the right hand side, we have the cathode, and at the left hand side, we have the anode. Always on cathode, there will be reduction, and we said it in the difference part of your galvanic cell and your electrolytic cell. So this is an example of electrolytic cell, and in your electrolytic cell also, the reduction will take part at cathode. If reduction is taking place, that means that your species is accepting electron and it is getting converted into solid form. And where it will be get converted into solid form, at that point your pure form will be obtained. Okay, so that is the reason we will take the pure copper on the cathode side and your impure sample on the anode side. I hope this question is clear to you. It's very simple to think about it. So moving on to the next question, and it is from the Kohlraasch law. You are given with the molar conductivity, limiting molar conductivity of ammonium hydroxide. And you have to say that this limiting molar conductivity of ammonium hydroxide will be equals to which of these equations? Remember, what is Kohlrausch's law? Kohlrausch's law says that for any given electrolyte, the limiting molar conductivity is equals to the contribution coming from the cation plus the contribution coming from the anion. Now, just try to break this down. What you will get? You will get lambda naught m NH4 OH is equals to lambda naught NH4 plus lambda naught m OH minus. Means contribution from NH4 plus also and contribution from OH minus also. Since the stoichiometric coefficient is 1, therefore we don't have to multiply the particular ionic molar conductivity with a number. Okay, it will be 1. Now, how can we get NH4OH? How can we get the addition of these two? So, for that you have to look upon this 4 species. Just break this down into ions and see that after the numerical, or I would say arithmetic progression, arithmetic solution, what you will get. So, break it down into NH4 plus OH minus, NH4 plus Cl minus, and HCl. And just do the calculation and see that which one is giving you NH4OH. So, I am getting answer as B. Anyone else who is interested to answer this question? So, it's a very simple one. What will be the answer for this question? Just try to break this limiting molar conductivity into contribution from particular ions. Okay, and then try to solve it. So let us assume that correct answer will be B. Okay, so let us see the correct answer. Okay, so this is B. How will solve it? It's very simple. You will apply the Kohlrausch's law here. So if you apply the Kohlrausch's law onto option number B, what you will get? You will get NH4Cl, lambda naught NaOH, lambda naught M of NH4OH, and lambda naught M of NaCl. Just break it down. So it will give you contribution from cation. For NH4Cl, it will be NH4 plus and it will be Cl minus. Similarly, for NaOH, it will be Na plus and OH minus. On the right hand side, if you see, it is NH4 plus and OH minus and Na plus and Cl minus. Now further, if you just rearrange it, you will get it as for NH4OH. Now, how are we telling this? If you take this Na plus Cl minus on the left hand side, what you will get? This Na plus and this Na plus will get cancelled out, and this Cl minus and this Cl minus will get cancelled out, and you will finally see that the addition of NH4Cl and NaOH subtracted with NaCl is giving you the limiting molar conductivity of ammonium hydroxide. Okay, I hope this is easy to get. Next question. Next is for the reaction which is half of H2 plus AgCl giving us H plus Cl minus plus Ag. You have to decide that which is the proper cell representation. You have 4 options given here. So first of all, just try to break this down into oxidation half reaction and reduction half reaction, and then write the reduction half reaction on the right hand side, oxidation half reaction on the left hand side, and see that whether your electron flow is correct or not, and you will get your final cell representation. Okay, so I am giving you some time to solve it. You can just comment your answer in the comment section. So what will be the correct answer? Simply just try to write the cell representation using the notation that your oxidation part will be on the left hand side and your reduction part will be on the right hand side. Anyone who got the answer? Okay, so we will try to select options one by one. Suppose we start from option number A. So in the given reaction, your Ag plus is going to Ag, right? So here on the left hand side, it is present in ionic form. On the right hand side, it is present in a neutral form. So can we see here that AgCl is present on the left hand side and Ag on the right hand side? No. So this is obviously not correct. First of all, it is containing a species which is NO3, which is not itself present in the equation also. But this would be a wrong way because in some cases ions get cancelled out. Let us move on to the other option. In the next option, your H2 is going to HCl. Yes, this can be seen in the equation as well. This hydrogen is getting oxidized to H plus and oxidation is written on the left hand side. So we can say that this part is correct and hence three options are now possible for the given equation, because in all of these three we are seeing H2 and HCl. Okay, in the option number D also we have KCl rather than HCl. So this is also out of the question. Okay, so we have two options left with us. Now if you look upon the two options, we have AgNO3 in the B option and in the C option we have AgCl. Now it is very obvious that your equation is only containing AgCl and not AgNO3. Okay, so we have taken solid AgCl and not aqueous AgNO3. Therefore, your correct representation will be option number C. So this is very easy to solve. So the correct option will be C. That means PtH2HCl aqueous giving us AgCl. Now one more question arises here. Why are we taking Pt here? Suppose in case of AgCl we take the Ag electrode, which is a silver electrode. But in case of your hydrogen we are taking a platinum electrode. So this is very obvious because hydrogen gas has no solid form at normal temperature. In place of electrode of hydrogen we take a inert electrode which is platinum. Got it? Inert, why? So that it cannot interfere with the reaction, and platinum because it can conduct electricity. So both the criteria are met by this platinum electrode. In many of the reactions you will see that, or in many of the cells you will see that you will take inert electrode rather than the actual electrode because the solid form of that particular thing is not available. Got it? Next, moving on further, we can say that in the particular reaction given, H2 is undergoing oxidation to form H plus and AgCl is going to Ag as it is going reduction. Therefore, your correct representation will be PtH2HCl on the left hand side and AgCl Ag on the right hand side. Next question. So, which of the following is not true? Four options are given here. In the first option, cathode is negative terminal in an electrolytic cell. So first of all, remember what is an electrolytic cell. In case of electrolytic cell, you have your non-spontaneous reaction carried out by an external factor, which is your electrical energy. And in that case, if you remember, then the left hand side is your what? Anode, and anode is taken as the positive terminal. Okay, anode is taken as the positive terminal, not the negative terminal. So it can be an incorrect option. Moving on to the B option, anode is positive terminal in a galvanic cell. So this is also not correct. Okay, third option, reduction occur at cathode in either of the cells. So this is not true. Okay, this is true because in both the cells, if you consider electrolytic cell or you consider galvanic cell, in both the cells, reduction is occurring at the cathode irrespective of the cell you are taking. Fourth option, oxidation occurs at anode. So this is also true. Now two options are there. Cathode is negative terminal and in the second case, anode is positive terminal. So if you remember the mnemonic, which is LOAN, from that mnemonic, it is very clear that anode is negative terminal and not your positive terminal. Okay, and opposite thing is seen in case of cathode. Moving on to the answer, so the correct option will be B. That means anode is positive terminal in a galvanic cell. So we can clearly say from this diagram also that this is your anode part which is present on the left hand side and this is your cathode part present on the right hand side. And here we can see clearly a negative sign and a positive sign. And this thing can also be remembered using the mnemonic, which is lone. That means on left hand side, oxidation will take place at anode and anode will be negatively charged. Okay, so L for lone, O for oxidation, A for anode, and N for negative terminal. Okay, is it clear to all of you? It's very simple. Moving on to the next question. So, question says that we are given with the reduction potential of Fe2 plus Fe and Sn2 plus Sn as 0.44 with a negative sign and minus 0.14 respectively. Further, you are given with a cell reaction where Fe2 plus is going to Fe and Sn is going to Sn2 plus, and you have to calculate the standard EMF. Got it? Now, it's very simple to do. What you have to do is to subtract the reduction potential of the species getting reduced minus the reduction potential of the species getting oxidized. Now just look upon the equation and decide that which species is getting reduced and which one is getting oxidized, and from there you can get your standard reduction potential for this EMF of this particular cell. 4 options are given here: plus 0.30, minus 0.58, plus 0.58 and minus 0.30. How you will do it? I have given you the formula also. You just have to decide that which species is getting oxidized and which one is getting reduced. What is the formula? E naught of the species getting reduced minus E naught of the species getting oxidized, or the reduction potential of the species getting reduced minus the reduction potential of the species getting oxidized. If you are getting your answer, it's very simple. It's just a subtraction. You will easily get your answer. You can just comment it in the comment section. Okay, so let us move on to the answer. The correct answer will be D, which is minus 0.30. How we'll solve it? First of all, we will write that what is given in the question. So, you are given with the E naught value of Fe2 plus Fe, which is minus 0.44 volts. Then after, you are given with the E naught value of Sn2 plus to Sn, which is minus 0.14. Now, how you will do it? At the cathode, we have the reduction. So, I have written it in the cathode and anode form. At the cathode, we have the reduction. So, E naught of cathode minus the E naught of anode. Next, if you look upon the equation, you can clearly see that Fe2 plus is going to Fe. Means this is the substance which is getting reduced by accepting 2 electrons. So, we will take the reduction potential of Fe2 plus Fe first of all, which is given here as minus 0.44. Okay. Next, your Sn is going to Sn2 plus. So, this is the species getting oxidized. Therefore, we will take it after the negative sign. So, minus 0.14. Now, it's a simple subtraction and you will get your answer as 0.30 with a negative sign. So, this is your standard EMF of the given cell. Is it clear to all of you? I hope it is very simple. Now, you can solve this question in a different way also. Rather than learning this formula, in some cases you can get confused that which should be taken at the left and which should be taken at the right. It's very simple. The next thing you can do is just see that which is the species getting oxidized. So here you can see that Sn is getting oxidized to Sn2 plus. So take the oxidation potential of this Sn and add it with the species getting reduced, which is Fe2 plus. But in the question, you are given with the reduction potential of Sn2 plus and not the oxidation potential of Sn. But I told to you that it's very easy to convert the reduction potential into oxidation potential. And what is the way? Just take the opposite side. So rather than taking the reduction potential of Sn2 plus, you can take the oxidation potential of Sn, which is 0.14, and then add it with the reduction potential of Fe2 plus. Then you will get your answer. So in both the cases, you are doing the same calculation but with a different sense. Okay, and this is the actual spirit of the formula itself. Got it? So what we do is we add the oxidation potential of the species getting oxidized with the reduction potential of the species getting reduced. And how do you find it? If 1 is given, you will simply reverse the sign. I hope this is clear to you. Now, this is your last question. You are given with 4 couples. So Ag and Mg, Ag and Al, Mg and Al, and Cu and Cr. Okay. So you have silver, magnesium, aluminium, then your copper and chromium. Next, you have to decide that out of these given species, which species cannot be obtained by electrolysis, or you can say which species cannot be purified by the electrolysis process of their aqueous solution. This is your question. Now you have an information also. So you are given with the order of the reduction potential for the given species in the equation or in the option. So you have Mg2 plus Mg, then you have Al3 plus Al, then you have Cr3 plus Cr, then you have Cu2 plus Cu, and Ag plus Ag. Means that this species has the highest reduction potential. Okay, got it? Then this one, then this one, then this one, and then lastly Mg2 plus and Mg. So how you will decide that which species has the greatest uh, way to go into the neutral phase and which species has the lowest tendency to go into the neutral phase? Now, with that thing, you can easily decide that which species cannot be purified using the electrolysis process. Because if you say that a given species has a very low tendency to go into the neutral phase, that means it will try to be in the gaseous, into the aqueous phase only. Okay, got it? So this is very simple to get. You simply have to decide that which one has the lowest reduction potential of all, and that will give you your answer immediately. Because this Ag, this copper and your chromium, all of these are very stable. So they will quickly convert from the ionic form to the neutral form, and they will be deposited onto the electrode. But if you consider your magnesium and aluminium, then they have a very low reduction potential, even lower than the water. So rather than getting reduced, it will get oxidized, and in turn of that, water will get reduced. Okay, is it clear to you? So this is basically the tendency of a species to go into the neutral form, and the reduction potential says that the species with the highest reduction potential has the highest tendency to go into the neutral form. And you can clearly say that copper and your silver and your chromium has this tendency, whereas your magnesium and aluminium has a low reduction potential. So it cannot be reduced easily, or you can say it cannot be gone into their neutral form easily. Therefore, they cannot be converted into the pure form using electrolysis. Therefore, what will be the correct answer? So out of this 4 couple, the correct answer will be magnesium and aluminium. So we can say that magnesium and aluminium has negative reduction potential. Okay, means it has a lower reduction potential than your hydrogen. Okay, and that is the reason that they cannot be obtained from the electrolysis of their aqueous solution. Now what will happen instead of that? Instead of getting magnesium and aluminium in the pure form, if you do electrolysis of this given species, what will happen? So due to their negative reduction potential, your water is reduced preferentially. Okay, over your magnesium and aluminium, your water will be reduced, preventing these metals from depositing onto the pure electron. Now, what will be the product? It means that your water is reduced more easily than the magnesium and aluminium ion, and as a result of that, you will see that there is a liberation of hydrogen gas. Okay, now just this is directly from your electrochemical series. If you don't know the electrochemical series, but still you can solve it, because out of these given species, one option would be correct, and that is very obvious. And you have your series of reduction potential. That means the species with the lowest reduction potential must be the one with the negative reduction potential. Okay. So what is happening here? your magnesium and aluminum is not getting reduced. Rather than that, your hydrogen is formed due to the reduction of your water. Okay. Now, how is your water reduced? So you know it very well from an ionic equilibrium that water is auto-ionized to some extent, and it has a concentration of H plus and OH minus as 10 to the power minus 7. Now that amount of your H plus will be converted into your H2, and that will lead to the liberation of H2 gas rather than the formation of pure magnesium and aluminum. Is it clear to you? Anyone who has a doubt in this part? Okay, so today we will try to solve the DPPs as well, which are given in our website. So anyone who has a doubt in this part, or is it clear to all of you? Okay, so just wait for a while. So now we will do DPPs on it. Okay, so this DPP of today's date will be solved today. I will request all of you to open the DPP along with me so that you can solve it with me. Got it? Just wait for a while. So here is your thing. So this is question number 1 of your DPP. So we are given with 20 minutes, but we will try to end it faster as much as questions we can solve, because we have our next maths class in a few minutes. So question says that if hydrogen electrode is dipped in two solutions, okay, one is of pH 4 and other of pH 6 at 1 atm pressure, and the salt bridge is connected, the EMF of the resulting cell is. Now this is an example of concentration cell. What do you mean by concentration cell? So concentration cells are those which have the same species on cathode and anode part, but the concentrations are different. Like in one we have H plus concentration of 10 to the power minus 4. On the right hand side we have a H plus concentration of 10 to the power minus 6. Okay, so it is directly coming from the pH formula. Now you have to say that what will be the EMF. So how do we calculate the EMF? So E cell is equals to E naught cell, okay, minus 0.0591. Since we have to take the standard condition, therefore we will take this value as 298 and it will give you 0.0591. Now let us write that what will be the reaction that will undergo. So we will go from H plus to half H2, and in that process one electron will be released. Okay, so this thing will be at your anode. Similarly, At cathode, what will happen? Reduction will take place. Half H2, okay, and half H2 will go to H plus and it will release one electron. So here electron will be on this side. Okay, so this will be your overall reaction in the case of given concentration cell. Now, next, what is the way to do it? It's very simple. You have to write the number of electron in the denominator here. So here it is 1, obviously. Then you have to take log Q, means the concentration of your oxidized part. So this is H plus present on the right hand side and H plus present on the left hand side. But the question is that which concentration you will take. Okay. What is the concentration that you will take so that you can get a right value. So what will be the concentration you will take for your anode and what concentration you will take for cathode? Anyone, can you tell me? Again, I am repeating it. So what concentration you will take at anode, because two concentrations are given here and you are not mentioned with that which will be cathode and which will be anode. So how you will take it? How you will approach this question? Anyone? Okay. So let me tell it for you. Here you will take it as 10 to the power minus 4. Here you will take it as 10 to the power minus 6. Just solve this thing. So this will be equals to 0. Why? Because E naught cell will be taken as 0 because both of the species are same. Next, it will be minus 0.0591. Then log 10 to the power 2 will be here. Okay. Okay, so this will be minus 6 and this will be minus 4. Sorry. Then next what will happen? You will get log 10 to the power minus 2. This minus 2 will be multiplied here and you will get it as 0.0591 multiplied by 2 log 10. Just solve this thing. So 2 9s are 18, 2 5s are 10, 1 11 and 0.0118. So if you just round this off, you will get it as 0.12, which is option number first. Okay, so in this way you can solve all of this question. So this was just a sample for you. Now our maths faculty will join you in a minute. Thank you for joining the session.
Hello everyone. So welcome to today's session of Crash Course. So today we will discuss Maxima and Minima, another application of derivative. Okay. So according to last 8 year, chapter weightage of application of derivative is 4.26%, and according to year-wise data, from the topic Maxima and Minima, there is one question in there 2024, one question in 2023, two question in 2020, and one question from 2019 to 2017 in each year of average and difficult level. Okay. In today's class, we will discuss at first maxima and minima of a function. If there is a function fx, then what is its maxima, maximum and minimum value? Okay. What are the critical points for that function? And how we can find local maxima and local minima for a function by using its derivative. Then second or higher order derivative test. What is the point of inflation? Nth derivative test. And then concept of global maxima and minima. How global maxima and minima is different from local maxima and minima. Okay. And some important result on maxima and minima. And after covering this theory, we will discuss some question based on maxima and minima. Okay. So let's start. So if we have a function fx, we define a function fx, and let x is equal to a be any point on its domain, then function fx attain a maximum at a point x is equal to a if there exists a neighborhood a minus delta a plus delta of a. A minus delta and a plus delta is just a neighborhood, it's an open interval that contains a point a, and it is a neighborhood of a. Okay, that is contains the point that lies around the point a. So the function fx attain a maxima at x equal to a if fx is less than a for all x belongs to this neighborhood a minus delta a plus delta for all x not equal to a, and where delta is very small quantity, small positive quantity, delta is greater than 0. Okay, so what does it mean? It means if around that neighborhood of a, for each value of x from that neighborhood, that is x is not equal to a, if fx, the functional value f of f, that x is less than fa, function value at a point a, then fa is the maximum value, and fx, that function, attain maximum at x equal to a. At that point, we are talking about a certain point. Okay, so the value fa is said to be maximum value of fx, and at a point x equal to a. In a similar way, we can define minimum for that function. So function fx attain a minimum at a point x equal to a if there exists a neighborhood around that point a, and that neighborhood is a minus delta a plus delta, where delta is very small quantity. So we just take an open interval around a point a which contain a, and this is the interval that contains a number around the point a. So if fx x come from this open interval where x is not equal to a. So if for all x from this neighborhood, it satisfies this condition that fx is greater than fa. It means fa, the function value at a, is the least value on that in neighborhood, then that fa is the minimum value of function fx, and fx attain the minimum at x equal to a. So it's just talking about a certain point. We're talking about that at a point x equal to a, that function attain a minimum. Okay. So let's see this graph. We have a function, we have a continuous function. So here the point A, B, C and D are the points of local maxima and local minima. So just take a particular point A. So around this point A, if we draw a neighborhood, take a neighborhood at a point A, then on that neighborhood, at a point A is the maximum value of fx. Okay. So point A is the point of local maxima for a function fx. In a similar way, point B, around point B, if we take a neighborhood, then on that neighborhood, the function value of B is the least value on that neighborhood. So B is the value of local minima. In a similar way, C is the local maxima and D is the local minima. These are the local maximum, local minimum. Okay. And from this graph, we can also observe that the point of greatest value and absolute maximum and least value and absolute minimum, this value are the least among all the minimum, local minimum, and the greatest value is the greatest value among the all local maximum. Okay. So the point at which the function attains either its maximum or minimum value, that point are called extreme point or turning point. And the value of the function at that extreme points are called the extreme values. Okay. So the point A, B, C, D are the extreme points or turning point, and value of the function at that point are the extreme values. Okay. So here A and C are called local maximum, and point B and D are called local minimum. Okay. Next is critical point. So what is critical point? So if you have function f and then a point, we define a function. So there must be a domain from where we define a function. So C is the critical point, then C is the point from the domain which either f dash C is equal to 0 or f is not differentiable is called a critical point of f. So if we have a function, we define a function. So a point from the domain where first thing, if f dash C is equal to 0, then C is critical point, or if at that point f is not differentiable, then that point is also a critical point. Okay. Next, if f is continuous. Now, if f is continuous and there is also another property that f dash C is equal to 0, then it implies that there must exist a neighborhood around a point C, that is C minus h, C plus h, where h is a very small quantity, very small positive quantity. So this is a neighborhood around the point C where your function f is differentiable. Okay. So if function is continuous and at a point C and f dash C is equal to 0, then we get a neighborhood around the point C where his function is differentiable. Clear? This is just a note. And at a critical point, the function, we get a local maxima and local minimum value for a function. Okay. Now the converse of above theorem need not be true. It means that is the point at which the derivative vanishes need not be a point of local maxima or local minima. For example, if your function fx is equal to x cube, then its derivative is When you differentiate x cube with respect to x, we get 3x square. So f dash x is 3x square, which vanishes at a point of origin. F0 is 0, but the 0 is not a point of local maxima and local minima. That are the point of inflection. Okay, so converse of the Earth theorem, it does not true. It means if we get f dash c is equal to 0, it doesn't mean that point is a point of local maxima or local minima. Okay. Now, first derivative test. There are certain method to find local maxima or local minima. So first one, the first derivative test. So if we have a function f and that function is defined on an open interval I, okay, and f be a continuous at a critical point c in f, okay. So what is the in previous slide we given important note, if a function is continuous at a critical point and f, that is f dash is equal to 0, then there exists a neighborhood around that c where the function is differentiable, okay. So if a function f and that is defined on an open interval I, okay, and f be continuous at a critical point c in I on that interval, then C, your critical point is point of local maxima. If, what is the condition? If we differentiate our function f and we find f dash x, and if f dash x change sign from positive to negative as x increases through c. And what does it mean? So, we just take a neighborhood around that point c, where let h is greater than 0, very small quantity, c minus h to c plus h. If from c minus h to h, our f dash is greater than 0, that is f dash x greater than 0 at every point sufficient close to and to the left of c, that means c minus h to c, and f dash is less than 0 at every point sufficient close to and to the right of c, then c is a point of local maxima. It means we just create a neighborhood around a c, c minus h to c plus h, and from if c minus h to c, f dash x is greater than 0, and from c to c plus h, f dash x is less than 0, then that point c is your point of local maxima. So if f dash x change sign from positive to negative for a point from c minus h to c, f dash x is positive, and from c to c plus h, f dash x is negative, then your point c, that critical point c, is your point of local maxima. Clear? Now, c is the point of local minima. When? What is the condition? If your f dash x change sign from negative to positive as x increases through point c, and what does it mean? As c is a critical point and f is continuous, we just create a neighborhood at a point c, that is c minus h to c plus h. So if from c minus h to c, f dash x is less than 0, and from c to c plus h, f dash x is greater than 0. Okay, that is f dash x is less than 0 at every point sufficient close to and to the left of c. Left of c means c minus h to c, and right of c means c to c plus h. So if the function f dash x change sign from negative to positive as x increases through a point c, then your point c is a point of local minima. Okay. Now, what if f dash x does not change its sign? It means on that neighborhood, f dash x does not change its sign. It has the same sign. Then the critical point c is neither a point of local maxima nor a point of local minima, and such point are called point of inflection. Okay, so we can understand this all these 3 points, this first derivative test, by this figure. So from this figure there are 4 critical points: c1, c2, c3 and c4. Your y is equal to fx is your function. Now what are the critical point where f dash x is equal to 0 and where function is not differentiable. So C1 and C2 are the points where f dash x is equal to 0, and C3 and C4 are the critical point where function is not differentiable. Okay, now first thing, if C is a critical point, let C1 is a critical point, and at C1, here if we take a neighborhood, then from C minus h to C1, C1 minus h to C1, f dash x is greater than 0. It means f dash x is greater than 0, it means positive. And from C1 to C1 plus h, f dash x is less than 0. So f dash x is changed its sign from positive to negative as x increases through C. So here C1 is a point of local maxima. Okay, as around C1, first function, the curve is increases, and then after C1 it decreases. So that point is your point of local maxima. Clear? For C2, as we can see, the sign of f dash x is changes from negative to positive. To the left of C2, it is negative, and to the right of C2, it is positive. So f dash x changes sign from negative to positive. Clear? So C2 is the point, is a critical point, and is a point of local minima. Clear? And C3 is a point of non-differentiability and is a point of local maxima, and C4 is a point of non-differentiability, but it is a point of local minima. Clear? And third point, if f dash x does not change its sign as x increases through C, then that C, that critical point, is a point of neither a point of local maxima nor a point of local minima. So this is your first derivative test. Clear? By just using the first derivative f dash x, we can find out is it the critical point is point of local maxima or point of local minima by see the sign of f dash x on the neighborhood of C1. Okay, clear? Now if C is a point of, now C is a critical point, and if C is a point of local maxima, then function value at that point C is your maximum value. Similarly, if C is a point of local minima, then function value at C, that is fc, is a local minimum value of f. So that's how we can calculate local maximum value and local minimum value of function f. At first we find a critical point, then we check the sign of f dash x around the point critical point. Okay, so here C1 is a point of local maxima and fc1 is local maximum value of function f, and C2 is a point of local minima and fc2 is a local minimum value of f. Clear? Now we will discuss second or higher order derivative test. Okay, so first step is we have a function fx, so differentiate that function and find f dash x and equate it to the 0. So when we equate it to the 0, we get f dash x is equal to 0, and when we solve this f dash x is equal to 0, we get its roots. Let's suppose that roots are a1, a2, comma dash dash dash. So this a1, a2 and dot 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 are the roots of f dash x is equal to 0. So these are the critical point for function f. Okay, so in step 1 we just find out the critical points by equating the f dash x is equal to 0. In second step, find f double dash x at x equal to a1. Just take x first critical point a1 and find f double dash x and at x equal to a1. If f double dash at a point a1 is positive, then fx is minimum at x equal to a1. Okay, so what is the second derivative test? First, you have a function fx, differentiate it and equate it to 0, and then find its roots. F dash x equal to 0, that's roots are the critical point, and then calculate f double dash x, that is differentiate f dash x one more time and check the sign of f double dash x at the critical points. So if at a critical point f double dash is positive, then on that point fx is minimum, and if on the critical point f double dash is negative, then fx is maximum at x equal to a1. It means on that critical point. Clear? This is the second derivative test. Now, let's suppose if at x equal to a1, f double dash a1 is equal to 0. Okay? So we go for higher order derivative test. Then we go for higher order derivative test. Now we calculate f triple dash x. We differentiate f 3 times. Okay? And if f triple dash at that critical point is not equal to 0, then that point has neither maxima nor minima. Okay? And if let's suppose f triple dash a1 is also 0, then we calculate fourth time differentiation of x. And if the fourth time differentiation of x is positive, then the function has minimum value at that point, and if it is negative, then it has a maximum value at that point. Clear? And if at the fourth derivative it is also 0, then we proceed in the same way. We calculate its higher derivative and check in same way. Okay? Now, what is point of inflection? We already discussed. So, at point of inflection, the point where neither maxima nor minima, it is not necessary that first derivative is 0. So, at a point of inflection, it does not necessary that first derivative is 0. Okay? But second derivative must be 0, or second derivative changes sign in the neighborhood of point of inflection. Clear? For the point of inflection, it does not necessary the first derivative is 0, but second derivative must be 0, or second derivative changes sign in the neighborhood of point of inflection. It means it can be goes from positive to negative on the neighborhood, or from negative to positive. Then that point is point of inflection. As from this figure, A is the point of inflection. If you have a graph, by graph you can easily tell which point are the point of inflection and which point are not. The point where the graph changes concavity, that point is point of inflection. At that point A, the function has neither maxima nor minima. Okay? Now, nth derivative test. Let f be a function, f be a differentiable function on an interval I, and a be an interior point of I. So if we have a function f, and we define on interval I, and we take a point from interval I. A is the point from interval I, such that we differentiate f n minus 1 times and take the value at a point A. So f dash A, f double dash A, f triple dash A, and so on, f n minus 1 A. We differentiate f n minus 1 time and substitute A, we get 0. A is the interior point of I, and we define f as a differential function on interval I. So we check for A, and when we differentiate n time that function, then the value at A, f n A exists and is non-zero. till n minus 1 value is 0, and when we calculate nth derivative of f at that point a is exist and it is non-zero, then if n is even and the nth derivative of function f at point a is greater than 0, then it implies the point a is a point of local minima. So what is nth derivative test? If we have a function f and it is a differential function, we define on an interval I and let a be an interior point of I such that we want to check, is it a point of local minima? So we just differentiate f n times, and if the value of this differentiation till n minus 1 is 0 and nth derivative of f exists at a point a and is non-zero, and if n is even and nth derivative of a at a point a is greater than 0, then your x is equal to a is point of local minima. What if n is odd? So if n is odd, then your point x is equal to a is a point of neither local maxima nor a point of local minima. Clear? So this is your nth derivative test. Now we will discuss some specific function. Result for some specific function. So first function is, if your function is of the type fx is equal to ax plus b by cx plus d. So the function from of this type, where we can take different value of a, b and c, d, has no local maxima or minima, regardless what is the value of a, b and c and d. Okay, specific result. And the function of the type like f theta is equal to sine m the power m theta into cos the power n theta attains its maximum value at theta is equal to tan inverse root under m by n. So at this theta, this function attain its maximum value. We can prove this. And third result, specific result, particular result based on circle. So if AB is a diameter of a circle, there is a circle and AB, we just take AB as a diameter of circle, and let C be any point on its circumference. So by using A, B and C, we create a triangle. Then the area of this triangle will be maximum if triangle is isosceles. It means if two sides of triangle are equal, then area of the triangle ABC will be maximum. Just a result. Now, till now we will discuss local maxima and local minima. Now, what is global maxima and minima? So let y is equal to fx be a function, be a given function with domain D. So D is the domain, and let closed interval AB is a subset of D. Then global maxima minima of fx in this closed interval AB is basically the greatest and least value of fx in closed interval AB. So now we'll discuss on an interval what is the maximum or minimum value on that interval. Till now we'll discuss on that on a particular point. We just take a neighborhood around that point and we say that function has a local maxima and local minima around that point at a particular point. But when we discuss at an interval like a function f, we define a function fx on a domain D and we just take an interval, closed interval AB on that domain. So when we discuss about a greatest and least value on that interval, then we say that value, that greatest and least value of that function on that interval, your global maximum and global minimum on that interval, not on a point. Okay. So important thing about global maximum minima. So if you want to find global maximum minima on closed interval AB, then this global maximum minima always occur at critical point of fx. We already discussed what are the critical point. So global maximum minima is always occur at the critical point, and that are within the closed interval AB, and also they can be occurred at the end points of the interval. So to find the global max and minima, we have to check its critical point as well as at the end point of the interval. Okay. So to find global max and minima of a function fx in this closed interval AB, first step is find out all the critical point of function fx in your closed interval. Okay. And how we can calculate the critical points? Just find out the first derivative of f and equate it to 0 and solve the equation and try to find out all the roots of f dash x equal to 0. That's root are the critical point for fx. Let's suppose these points are c1, c2 and cn. In second step, find the value of function at this critical point. That value are fc1, fc2 dot 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 fcn, and also find the value of function at the end point of domain, that is f and fv, because global maxima and minima in the closed interval AB would be occur at critical point of fx or at the end points of the interval. So to find the global max and minima, we have to calculate the function value at the critical points as well as at the end point of the domain. So we just find fa and fb. Okay. So in a step 3, let capital M1 is the value of global maxima or greatest value, and M2 as global minima or least value. Then M1 can be found by just take maximum value from the FA, FC1, FC2 till FCN and FV. So the maximum values from all these values of F is your global maxima, and least value, minimum value from all this your minimum, global minimum of the function fx. Clear? So to find the global maxima and minima for a function f on a particular closed interval AB, at the first step find all the critical point. On a second step, calculate the function value at the critical point as well as at the end point, and then compare and get the maximum values from all this value. That maximum value is global maxima or greatest value, and the minimum value from all this your global minima or least value. Clear? So some important result on maxima and minima. First one is maxima and minima occur alternatively, that is between two maxima there is one minimum and vice versa. Okay, it means between always two maxima there must be a minimum value, and between two minimum value there must be a maximum value. Okay, so first just if we take local maxima, then we get local minima, local maxima, then again local minima, local maxima, local minima. In such a way we find out the maximum, local maximum, local minimum value for a function. Now second result, if your function value is tending to infinity as x tending to a or b, so when we take the value of x to a to b, our function value is tending to infinity, and if f dash x is equal to 0 only for one value of x, say c, between a and b. So what is this? If fx tending to infinity as x tending to a or b, and there is only one point on that interval a to b where f dash x is equal to 0, then that point necessarily the point of local minima, and the value fc at that point c is necessarily the minimum and least value. Third result, if the function value fx tending to minus infinity as x tending to a or b, then fc is necessarily the maximum or greatest value. Okay, so if our function tending to minus infinity at a point x equal to a as x tending to a or x tending to b, and there is a point, a single one point, only one point, such that f dash x is equal to 0 on that point, then C is must be necessarily the point of local maxima, and the value fc is necessarily the maximum or greatest value for function fx. Okay. Now, the stationary point are the points of the domain where f dash x is equal to 0. So, if we get the first derivative as 0, that is f dash x is equal to 0, then the points are stationary. Okay. Let's summarize. So, what are the maximum and minimum value? If we have a function fx, then we said it has a maximum value at a point A if there exists a neighborhood, and on that neighborhood, that value, the function value at A is maximum, then this is your maximum value. In a similar way, we can define minimum value. What are the critical point? Critical point are the points where it is points from the domain where f dash c is equal to 0, and at that point f is not differentiable, then that point is a critical point. How we can find local maximum, local minima? First derivative test is find f dash x and equate it to 0, then equate it to 0 and solve it for its roots, find its root, that means find its critical point, then find its second derivative and check the sign of second derivative at critical points. If it is positive, then fx is minimum at x equal to a, and if it is negative, then fx is maximum at x equal to a1. What are the point of inflection? The point where neither maxima nor minima, and at a point of inflection, it is not necessary that first derivative is 0 and the second derivative either must be 0 or second derivative change sign in the neighborhood of point of inflection. Okay. When we're talking about global maxima and minima, we are talking about maximum or minimum value of function, not at a point but at a interval, like a close, we are talking about at a closed interval AB. Okay. And there are some result. Maximum minimum occur alternatively between two maxima, there is one minimum and vice versa. Okay. And if fx tending to infinity as x tending to a to b, and if there is a point C between a to b, and on that point if fx equal to 0, then that point is must be a point of local minima. And if it tending to minus infinity as x tend to a and b, then fc must be a point of maximum or greatest value. And what are the stationary point? Where f dash x is equal to 0. Okay. So just wait for a moment. Now we will discuss. Now we will practice some question based on maxima and minima. Okay. So now we'll practice some question based on maxima and minima. So first question. If f is defined as fx is equal to x plus 1 by x, then which of the following is true? So we have a function fx, and what is the definition of function? It is defined as fx equal to x plus 1 by x. Then we ask for which of the following statement is true. Options are local maximum value of fx is minus 2. Option B, local minimum value of fx is 2. Option C, local maximum value of fx is less than local minimum value of fx. All the above are true. Okay. So we have to find local maxima or local minimum value of function fx. Clear? So to find the local maxima and local minimum, we use the derivative. First, differentiate the function fx and equate it to 0 to find the critical points. Okay. And when you have the critical points, we check the sign of f double dash. So differentiate fx f dash x again, and find the f double dash x, and then check the sign of f double dash x at the critical point, and according to the sign, fx has local maxima and local minima. Clear? So at the first step, find its critical point, then differentiate it. Again, find the double derivative and check the sign and figure out which option are correct. Okay. So try. What are the critical points? Bank. Okay, let's solve. So correct answer is option D. All the above are true. Let's verify it. Correct. So let y is equal to x plus 1 by x. Okay. And to find its critical point, we just differentiate y with respect to x. We find f dash x. So dy by dx is equal to differentiation of x is 1 and differentiation of 1 by x is minus 1 by x square. So dy by dx is equal to 1 minus 1 by x square. And to find critical point, we equate it to 0. So dy by dx is equal to 0. So we get 1 minus 1 by x square is equal to 0. And when we simplify it, we get x square is equal to 1. Now to solve for x, to find the root of equation dy by dx is equal to 0, that are the critical points, we get x is equal to plus minus 1. So there are two critical points, plus 1 and minus 1. Step 1 is complete. In second step, now again differentiate dy by dx we get d2y by dx2. Differentiation of 1 is 0 and differentiation of minus 1 by x square is 2 by x cube. Okay. So now we check the sign of d2y by dx2 at the critical points. So at x equal to 1, the value of d2y by dx2 is 2 by x cube, that is 2 by 1, that is 2, that is greater than 0. And at x equal to minus 1, the value of d2y by dx2 is 2 by minus 1 the power cube, that is 2 by minus 1, that is minus 2, and this is less than 0. So the double derivative, that is f double dash x, is greater than 0 at a critical point x equal to 1, and it is less than 0 at a point x equal to minus 1. Okay. So as is greater than 0 at 1 and less than 0 at minus 1. So at x equal to minus 1 is a critical point, and at this point this double derivative is less than 0. So this is a point of local maxima. So y has a local maximum value at x equal to minus 1, and that value is minus 2. Clear? And as the double derivative is greater than 0 at x equal to 1, so 1 is the point of local minima and local minimum value is 2. Okay. And as here local maximum value is minus 2 and local minimum value is 2. So it might be possible that local maximum value can be less than local minimum value, because we are talking about at a certain point, maximum minimum value at a point. We are not talking about the global maximum and global minimum. Okay. Therefore, the local maximum value is minus 2 and local minimum value is 2, and that is local maximum value is less than local minimum value. So all three are correct. So all the above are true. Clear? Very good. What's correct? Now second question. Question number 2. If the sum of two number is 3, then the maximum value of the product of the first and the square of second is, options are 4, 1, 3 and 0. Okay. So two number, let's suppose we have two number x and y. So first statement, sum of two number is 3, that is x plus y is equal to 3. So we can write y in terms of x as y is equal to 3 minus x. So we have two number, first number is x and second number is 3 minus x. Now then we have to find maximum value of the product of first and square of second number. Product of first number is x and square of second number 3 minus x whole square. So what is the product? X into 3 minus x square. So if you suppose product as a function, let p is equal to x into 3 minus x square. So we have to find the maximum value for that function. Okay. So just differentiate that function, x into 3 minus x whole square, and when you differentiate it, we find out f dash x equated to 0. We get the critical points for that function, and when you have the critical point, then again differentiate and find f double dash x and check the sign of f double dash x at that critical point, and according to the sign we can find the maximum value and minimum value for that function. Clear? So try. What are the critical points, Varsa? Okay, let's check. Correct answer is option A, 4. So let two number be x and 3 minus x, as the sum of two number is 3. So if we take x and y as two number, then x plus y is 3. So y can be written as 3 minus x. So we have two number x and 3 minus x. Okay. So let then the product of these two number is product of first and square of second. So let p is equal to x into 3 minus x whole square. Now to find its critical point, we just differentiate this p with respect to x. So we get dp by dx is equal to, now what is the product rule of differentiation? We have two function here, x and 3 minus x whole square. So for first, differentiate 3 minus x whole square and take x as it is, plus differentiation of x into 3 minus x whole square. So we get minus 2x, differentiation of 3 minus x whole square is 2 into 3 minus x into minus 1. So we get minus 2 into 3 minus x into x, that is minus 2x 3 minus x, plus differentiation of x is 1 into 3 minus x whole square. So when you simplify it, just take 3 minus x is common, we get dp by dx is equal to 3 minus x into 3 minus 3x. And calculate its second derivative. So d2p by dx2 is 6x minus 12. Just multiply this and we know the how we can differentiate the polynomial. Simple differentiation. So when we differentiate, we get 6x minus 12. You use this in second step. Now to find its critical point, we just equate dp by dx is equal to 0. And from here, we get 3 minus x into 3 minus 3x is equal to 0, that is x equal to 3 and 1. So 3 and 1 are the critical point. Okay, clear? Any doubt? So 3 and 1 are the critical point. Now we check the sign of d2p by dx2 at this critical point. So at x equal to 3, d2p by dx2 is equal to, just substitute x equal to 3 in place of x, we get 18 minus 12, that is equal to 6, and this is greater than 0. So as d2p by dx is greater than 0 at this critical point, so this is the point of local minima. Okay, and at x equal to 1, d2p by dx2 is minus 6, and this is your less than 0. So as the second derivative is negative at x equal to 1, this corresponds to a local maxima. When your second derivative is negative, it corresponds to a local maxima, and when your second derivative is positive, then that critical point corresponds to a local minima. So x equal to 1 is point of local maximum. Now to find the local maximum value of this product, just substitute x equal to 1 on the function p. So p is equal to x into 3 minus x whole square And this is equal to 1 into 3 minus 1 whole square, that is 1 into 2 square, and that is 4. So 4 is the maximum value of product of first and square of second number, where addition of this two number is 3. Clear? Okay, question number 3. So if y is equal to a log x plus bx square plus x has its extreme value at x equal to 1 and x equal to 2, then ab is equal to, options are 1, 1 by 2, 1 by 2 and 2, 2 comma minus 1 by 2, minus 2 by 3 and minus 1 by 6. Okay. So we have a function y is equal to a log x plus bx square plus x, and it is given that this function has an extreme value at x equal to 1 and x equal to 2, and we know that any function has its extreme value at a critical point. So x equal to 1 and x equal to 2 are the critical points. Okay, and what is the definition of critical point? At the critical point f dash x equal to 0. So use that concept that at a critical point f dash x is equal to 0. So just at first find the first derivative of y and then equate it to 0, that is dy by dx is equal to 0 at x equal to 1. So just substitute x equal to 1 on the differentiation and equate it to 0. We get an equation on a, b, and also substitute x equal to 2 on dy by dx. We again get an equation on a and b, and when we solve the both equations, you get the value of a and b. Okay, so try. Okay, let's solve. Correct answer is option D, minus 2 by 3 comma minus 1 by 6. So given function is a log x plus bx square plus x. So when you differentiate this with respect to x, dy by dx is equal to a by x. Differentiation of log x is 1 by x, so a by x. Differentiation of term bx square is 2bx, and differentiation of x is 1. So dy by dx is equal to a by x plus 2bx plus 1. Okay. Now dy by dx is equal to a by x plus 2bx plus 1. Now we know that as x equal to 1 and x equal to 2 are the critical point. So at that point dy by dx is 0. So when we substitute x equal to 1 on the equation dy by dx equal to a by x plus 2bx plus 1, we get 0. So just substitute x equal to 1, we get a plus 2b plus 1 is equal to 0. That is a is equal to minus 2b minus 1. Okay. Now x equal to 2 is also a critical point. So substitute x equal to 2, we get a by 2 plus 4b plus 1 is equal to 0. Now substitute the value of a from above equation to this equation, we get minus 2b minus 1 by 2 plus 4b plus 1 is equal to 0. And when we simplify this, we get minus b plus 4b plus 1 by 2 is equal to 0. That is 3b is equal to minus 1 by 2. That is b is equal to minus 1 by 6. And a is equal to minus 2b minus 1. So from here we get a is equal to 1 by 3 minus 1, that is minus 2 by 3. So the value of a is minus 2 by 3 and value of b is minus 1 by 6. Okay, clear? Any doubt? Okay, next question. The function fx is equal to a cos x plus b tan x plus x has extreme value at x equal to 0 and x equal to pi by 6. Question number 4 is similar to question number 3. This function has extreme value at x equal to 0 and x equal to pi by 6. So 0 and pi by 6 are the critical points. Okay. Then what are the value of a and b? A is option A is minus 2 by 3 and b is minus 1. Option C, A is 2 by 3 and b is minus 1. Option C, A is minus 2 by 3 and b is 1. And option D, A is 2 by 3 and b is 1. Okay. So to solve this, just apply the same way we solve the question number 3. Differentiate the function and get f dash x equated to 0 at the point of x equal to 0. Why? 0 is the critical point, pi by 6 is the critical point. So f dash x is 0 at x equal to 0 and f dash x is 0 at pi by 6. And when we substitute x equal to 0 and pi by 6 on f dash x, we get two equations on a and b. And when we solve the both equation, we get the value of a and b. Okay. So try. F dash x is equal to, what is the differentiation of cos x and tan x? Okay, option A. Okay, let's check. Very good. Correct option is option A. That is A is equal to minus 2 by 3 and B is minus 1. So let's solve. We have in function fx is equal to A cos x plus B tan x plus x. And when we differentiate it with respect to x, we get f dash x is equal to minus A sin x plus B sec square x plus 1. Differentiation of cos x is minus sin x and differentiation of tan x is sec square x. Okay. Now, as 0 and pi by 6 are the critical point, so f dash 0 is 0 and f dash pi by 6 is also 0. So just take x equal to 0 for f dash x, we get b plus 1 is equal to 0. Why? Sin 0 is 0 and sec 0 is 1. So you get b plus 1 is equal to 0. And when we substitute pi by 6, Sin pi by 6 is 1 by 2, that is minus a by 2, and sec pi by 6 is 2 by root 3, that is 4b by 3 when we square it. So we get minus a by 2 plus 4b by 3 plus 1 is equal to 0. So from first equation we get b is equal to minus 1, and when we substitute b is equal to minus 1 into the second equation, we get a is equal to minus 2 by 3. Okay? Clear. Now question number 5. The minimum radius vector of the curve 4 by x square plus 9 by y square is equal to 1 is of length a is equal to 1, b is equal to 5, c is equal to 7, and d is equal to none of these. Okay? So let's solve it. Correct answer is option B, that is 5. Given curve is 4 by x square plus 9 by y square is equal to 1. Now, we know that minimum radius vector of the curve a square by x square plus b square by y square is equal to 1 is a plus b. Okay? We can find out this by just take x is equal to r cos theta, y is equal to r sin theta, substitute into this and solve the equation, and we get the equation and differentiate that function to get f dash x equated to 0 and get the critical point. And on that critical point, when you find the minimum value for the function a square by x square plus b square by y square is equal to 1, so for this curve, the minimum radius vector is a plus b. Okay? Now, comparing given equation with this equation, a square by x square plus b square by y square is equal to 1, we have a is equal to 2 and b is equal to 3. So, minimum value is a plus b, that is 2 plus 3, that is 5. Okay. So, the radius vector has minimum value of 5. You can prove this result that minimum radius vector of the curve a square by x square plus b square by y square is equal to 1 is a plus b. Okay. Now question number 6. The function fx is equal to 4x cube minus 18x square plus 27x minus 7 has option A 1 local maxima, option B 1 local minima, option C 1 local maxima and 2 local minima, and option D neither maxima nor minima. Okay. So correct answer is option D, neither maxima nor minima. So to solve this question, we first differentiate, find its critical point, and then apply the derivative test. Okay. Let's solve. Given function fx is 4x cube minus 18x square plus 27x minus 7. So when we differentiate it with respect to x, we get 12x square minus 36x plus 27. So we can write, just take 3 as common. So 3 into 4x square minus 12x plus 9, and we can write it as 3 into 2x minus 3 whole square. Okay. Now when we equate f dash x is equal to 0, so from here we get x is equal to 3 by 2. So 3 by 2 is the critical point. First step is complete. Now, since f dash x is greater than 0 for all x, as f dash x is 3 into 2x minus 3 whole square, and 2x minus 3 is square, it is always positive, 3 is always positive. So f dash x is always positive, always greater than 0 for all x. That means f dash x does not change its sign. And it means x equal to 3 is a point of inflection. At x equal to 3 by 2, neither a point of maxima nor a point of minima. So when we check the sign of f dash x around the point 3 by 2, then the sign of f dash x is always positive, because 3 into 2x minus 3 whole square, it is always positive, so f dash is always positive. So 3 by 2 is a point of inflection. It has neither a point of maxima nor a point of minima. And as 3 by 2 is the only critical point, so the function has neither maxima nor minima. So correct answer is option D. Clear? So in today's lecture we covered maxima minima application of a derivative, and we practiced some question based on maxima and minima. Clear? Any doubt? Okay, then thank you. I hope the lesson was helpful. Hello everyone, welcome to today's lecture. In today's lecture, we are going to learn about thermal properties of matter and thermodynamics. This is theory part 3. Alright, this is our disclaimer. So, if we talk about the trend analysis in JEE examination of the chapter kinetic theory according to last 5 years, so we can say overall weightage is 3.9%. Alright, if we talk about the yearly quotient distribution, so we can say in 2024 question asked from average kinetic energy. Okay, and number of questions 1. And if we talk about their difficulty level, so we can say question was average. Similarly, in 2023 question asked from VRMS and V average. Okay, number of questions 1 and their difficulty level average. In 2022, question asked from root mean square speed calculations. Number of questions 1 and the difficulty level of the question was average. Similarly, in 2020, question asked from specific heat capacity of the gases. Number of questions 1 and the difficulty level average. Okay. All right. So in today's lecture, we will cover first kinetic theory of gases, then assumptions of kinetic theory of gases. After that, we will learn work done on compressing a gas. Then we will discuss kinetic theory and temperature. Then concept of pressure. Then various speeds of gas molecules. Then degree of freedom. Then law of equipartition of energy. Alright. Then specific heat capacities of the gases. Clear? Okay. So after that, we will discuss specific heat at constant volume and look at its definition and formula. Next, we will study specific heat at constant pressure, then specific heat in terms of degree of freedom, then mean free path, and last we will see Avogadro's number. Alright? Yes or no? So these are the topics of the today's lecture which we will cover one by one. Okay?
So today we will understand the kinetic theory of gases. All right. Okay. So let's start today's lecture. So here we will discuss about kinetic theory of gases. So this theory, kinetic theory of gases, connects the macroscopic properties of gases such as pressure, temperature, and volume with microscopic properties of the gas molecules such as speed, momentum, and kinetic energy of molecules. All right. So we can say, according to this theory, gas molecules are very small and move very rapidly. All right. So these molecules move randomly in any direction, or we can say every direction. And when they collide with the walls of the container, they exerts a force. Okay. So uh, which creates pressure. Okay. So as shown in the figure, look at here. So here, gas molecules are present in the container. Okay, and gases move randomly in any direction and exert a force on a wall of the container. All right. Okay. So gases exerts pressure on the wall of the container. So this is our kinetic theory of gases. Now here we will see some assumptions of kinetic theory of gases. Okay. So we can say our first assumption is gas is made up of tiny particles which are called molecules as shown in the figure. All right. So the size of the molecules or particles are very small, and the distance between them known as intermolecular spacing is much greater than their size. Okay, gas molecules are identical, that is similar. Okay, they are spherical, rigid, and perfectly elastic point masses. Point mass means very small mass. Okay, like a dot. So elastic means that when they collide, okay, there is a no loss of energy in the case of elastic, only their direction changes. All right, molecules always move rapidly in random directions, this is our next assumption, and collide with each other. So in these collisions there is a no loss of energy, only the molecules change their direction. The next one is the duration of a collision between two molecules is a very short, meaning it is too brief, that it can be ignored comparison to the time interval between one collision and the subsequent collision. Okay, so we can say molecules spend most of their time moving freely from one collision to next. Next assumption is the number of collisions in a unit volume remains constant. All right, and there is a no attractive or repulsive force between molecules, meaning they do not attract or repel. These assumptions are the basic pillars of kinetic theory, okay, which help in understanding the properties and behavior of gas. The next assumption, the effect of gravitational attraction between gas molecules is very small because the mass of the molecules is very small and they move very rapidly. The next assumption is molecules continuously collide with the walls of the container. So as a result of which their momentum changes. All right. Next assumption is this change in momentum is directly transferred to the walls of the container, due to which gas molecules exert pressure on the walls of the container. Okay, and inside the container the density of gas remains approximately constant everywhere. Okay, meaning the gas is uniformly distributed everywhere. All right. So students, these are the some assumptions for an ideal gas in the kinetic theory of gases. Okay. Next, work done on compressing a gas. So now we will study about the work done that is required to compress the gas. So when a gas is compressed and its volume changes, then some work is done on the gas as shown in the figure. So in the figure here, look at here, this figure, this one. You can see a cylinder and piston arrangement. Okay, so now some gas is filled in this cylinder and when we apply pressure on the piston from outside, the piston moves inwards and there is a change in volume which is represented by delta V. So the formula for work done is W equal to P into delta V. Okay, and delta V is equal to change in volume of the gas. Alright, work done on compressing a gas. So when two ideal gases mix, their mixture also behave like a new gas. Alright, so whose properties depend on the properties of both gases. Now let's understand it in detail. First, how do we calculate the molar mass m of the mixture? So molar mass is the total number of molecules in 1 mole of a gas when we mix two gases with the moles n1 and n2. So the molar mass of the mixture is weighted average of the molar masses m1 plus m2, m1 and m2, okay, of the both gases. Therefore, the formula is m equal to n1 m1 plus n into m2, n into m2 divided by n1 plus n2. This means that if one gas has one more molecules, its molar mass will have a greater effect on the mixture. Now let's talk about specific heat capacity. The specific heat capacity tells us how much heat energy is required to raise the temperature of 1 mole of a gas by 1 degree. Okay, so here we consider two types of specific heat. Uh, First, uh, at constant volume Cv and at constant pressure Cp. Okay, so when gases are mixed, the Cv of the mixture is mole weighted average of the Cv of both gases. So Cv equal to N1 Cv1 plus N2 Cv2 divided by N1 plus N2. Similarly, we have a one more formula, specific heat capacity of mixture at constant pressure, that is Cp equal to N1 Cp1 plus N2 Cp2 divided by N1 plus N2. This means that heat capacity of the mixture lies between the heat capacities of two gases according to their mole fractions. Okay, everyone, clear? Yes or no? Now the heat capacity ratio gamma, which is Cp upon Cv, the formula to calculate for a gas is gamma equal to N1 Cp1 plus N2 Cp2 divided by N1 Cv1 plus N2 Cv2. Okay. On the another equivalent form for gamma can also be calculated, which relates to the moles and gamma. Okay, so the values, gamma values of individual gases. So it will be uh, n1 plus n2 divided by gamma minus 1 is equal to n1 divided by gamma minus 1 equal to n2 divided by gamma 2 minus 1. This means that the heat capacity ratio of the mixture is formed by the combination of the heat capacities ratio of the both gases. In short, we can say when we mix two ideal gases, the molar mass, specific heat capacities, and heat capacity ratio of the mixture are calculated through the weighted average of the individual values of those gases and their mole numbers. All right. Next is kinetic energy and temperature. So in ideal gas, molecules are point particles, yes or no, which only possesses translational motion, meaning they move straight from their position, and due to this their kinetic energy is also solely translational kinetic energy. Okay, so the translational kinetic energy of a molecule is 1 by 2 mv square bar equal to 3 by 2 kt square. Okay, here m is the mass of the molecule and v square bar is the square of the average velocity of the molecule, and k is the Boltzmann constant, and t is the temperature. This means that the average kinetic energy of each molecule is equal to the translational kinetic energy of that molecule. So the average kinetic energy per molecule is equal to 3 by 2 kT. And we can express the total average kinetic energy of a gas also in terms of pressure P and volume V. So the average kinetic energy of gas is equal to 3 by 2 into PV. The average kinetic energy of a molecule can be written in the terms of Avogadro's number. So and goes gas constant. Okay, so the average kinetic energy per molecule equal to 3 PV divided by 2 Na is equal to 3 RT divided by 2 Na. So when we divide the average kinetic energy of the gas by Avogadro's number, we get the average kinetic energy per molecule. The next formula is average kinetic energy per mole. So when we talk about 1 mole of gas, its average kinetic energy is 3 by 2 RT, that is equal to average kinetic energy per mole. This is obtained with the help of the ideal gas equation. As we know, the average kinetic energy of a gas is 3 by 2 PV, which we can write as 3 by 2 nRT, and for 1 mole of gas n will become 1 and we will get 3 by 2 RT. Okay, and if we calculate the average kinetic energy per mole per unit volume, then it is average kinetic energy per volume is equal to 3 by 2 into P, and we know that the average kinetic energy of gas is 3 by 2 PV, and if we divide this by volume V, then we will get the average kinetic energy per unit volume. Okay everyone, next is concept of pressure. So molecules of an ideal gas move rapidly in all directions and continuously collide with the walls of the container. Yes or no? So when molecules collide with the wall, their momentum changes, and this change in momentum creates pressure on the walls of the container. Okay. So the relation for pressure P given by P equal to 1 by 3 into M into N V square RMS divided by V. Okay, this means that the pressure is directly proportional to the product of mass of the molecules, their mean square velocity, and their number, and inversely proportional to the volume. All right everyone, so now we define here uh, capital M is equal to small m into capital N, which is the total mass of a gas in the container. So further simplifying, we get PV equal to 1 by 3 mv square bar, which is equal to 1 by 3 into 2 divided by 2 into mv square bar, which is equal to 2 by 3 into 1 by 2 mv square bar. Okay, here m equal to m into capital N is the total mass of the gas molecules in the volume V of the container, and V square RMS is equal to V square bar mean square velocity of the molecule. M is the mass of each molecule and E is the total average kinetic energy. Alright everyone, any doubt here? Yes or no? Okay, so all these formulas are very important. Alright, now the formula for kinetic energy E is E equal to 1 by 2 mv square bar. Therefore, we can write PV equal to 2 by 3 into E. This means that the product of gas pressure and the volume is directly proportional to the total average kinetic energy of the gas. That is, the greater the kinetic energy of the molecules, the greater the gas pressure will be on the walls of the container. So, this formula is an important result of kinetic theory that relates the pressure of the kinetic energy of the molecules. Alright, clear? Any doubt here? Karthik, VK, Varsha? Varsha, doubt any here? Now let's understand the different types of speeds of gas molecules, which are very important in kinetic theory. Okay. So first is root mean square speed. It is defined as the square root of the mean square of the speed of different molecules. So the formula is V RMS equal to under root V1 square plus V2 square plus V3 square plus so on divided by N, which is equal to under root V square bar. And from the expression of pressure P equal to 1 by 3 rho V square RMS, uh, rho is the density of the gas. So we can write Vrms in different forms. Vrms is equal to under root 3p divided by rho, which is equal to under root 3pv divided by m. Okay. Okay. So let's see our next formula. So here from the expression of the pressure, we get Vrms is equal to under root 3 kT divided by m. So now if we talk about the most probable speed, this is the speed possessed by the maximum number of molecules. The greater the number of molecules move at this speed, its formula is Vmp equal to under root 2p divided by rho is equal to under root 2RT divided by m naught, which is equal to under root 2 kT by m. Okay. Third is average speed. So this is the simple arithmetic mean of the speeds of the molecules. It means we add the speed of all molecules and divided by the total number of molecules. So V average is equal to V1 plus V2 plus V3 plus V4 plus so on divided by N. N is the total number of molecules. Its formula can be defined from the kinetic theory, which is as follows: V average equal to under root 8p divided by rho into pi, which is equal to under root 8 RT divided by pi into m naught, which is equal to under root 8 kT by pi m. Alright. So these three speeds are directly proportional to temperature, meaning that when temperature increases, the speed of molecules also increases. Okay. Next is degree of freedom. The degree of freedom means the number of independent motions or movements that a molecule can perform without any restrictions. So for monoatomic gas like helium has 3 degree of freedom because it can only move in 3 directions: x, y, z and 3 x, y, z. Okay, so therefore F equal to 3. And for diatomic gas uh, like oxygen gas has 5 degree of freedom. Okay, so it can also perform 2 rotational motions in addition 2 plus 3 translational motion. All right, so degree of freedom is equal to 5, F equal to 5. For triatomic gas is non-linear like hydrogen gas, hydrogen or water, H2O, suppose H2O. All right, then it has 6 degree of freedom, meaning 3 translational plus 3 rotational. Therefore F equal to 6, and this is the case for non-linear. Next is for triatomic linear gas like CO2. So then it also has 5 degree of freedom, meaning 3 translational plus 2 rotational. Therefore F equal to 5. All right. All these values are at moderate temperature, meaning when the vibrations of molecules are not considered. Now at high temperatures, the vibrations of molecules also become important. So the atoms of molecules vibrate around their positions, and each vibration is a different mode. One vibrational mode gives two vibrational degree of freedom. Okay. So at high temperature, for an atomic non-linear molecule, the total degree of freedom will be 6 plus x. And for n atomic linear molecule, total degree of freedom will be 5 plus x. Here there are the x vibration degree of freedom. So a diatomic molecule has only one vibrational mode. Therefore x equal to 2 because one mode gives 2 degree of freedom. All right. Any doubt here? Yes or no? Clear? Next is law of equipartition of energy. So let's see the law. The law of equipartition of energy states that in thermal equilibrium, each degree of freedom is associated with uh, an average energy of 1 by 2 kT. This means that the total energy of the system is equally distributed among all possible energy modes, and each mode has an average energy of 1 by 2 kT, or we can say 1 by 2 kVT, where kV or K is the Boltzmann constant and T is the absolute temperature. Now, when we talk about the vibrational motion of molecules, atoms oscillates back and forth around their equilibrium position. So during this oscillation, the energy of atoms exists in two forms: kinetic energy and potential energy. So kinetic energy of an atoms is proportional to the pressure, proportional to the square of their speed, uh, that is v square, and the proportional and the potential energy of the atom is proportional to the square of their displacement. Okay, that is x square. All right. So both the terms are quadratic, meaning the energy expression contains square terms of velocity and displacement. So according to equipartition, each quadratic term is considered a degree of freedom, which is understood as an independent mode of energy in the system. Therefore, a vibrational mode contains two quadratic terms, kinetic energy and potential energy, which means that a vibrational mode provides two degree of freedom. All right. So each degree of freedom receives 1 by 2 kT energy. So the energy for a vibrational mode is 2 into 1 by 2 kT, which is equal to kT. Yes or no? So this means we can say the average energy of a vibrational mode is double compared to the translational or rotational modes, because only uh, they only have a kinetic energy distribution or contribution. So this concept is very important for understanding the heat uh, capacity of molecules, because vibrational modes significantly increase the total energy of the system, specifically at high temperatures where vibrations are more active. So kb equal to here 1.38 into 10 raised to power minus 23 joule per kelvin, and T is the absolute temperature. All right. Now we will study specific heat capacity, specific heat of the gases. So we have two types. First, specific at constant volume. Second, specific at constant pressure. So first, specific heat at constant volume. We can say specific heat of gas at constant volume means the quantity of heat required to raise the temperature of a unit mass of gas by 1 degree Celsius or 1 Kelvin when the volume of gas is kept constant. That is, mathematically we can say if it is written as Cv equal to delta QV divided by m into delta V. Here delta QV is the heat supplied at constant volume, m is the mass of the gas, and delta T is the change in temperature. Now, for if we consider 1 mole of gas, molar specific heat is defined. Molar mass is denoted by m. So, thus mCv equal to m into delta Q into V divided by m into delta T, which is equal to 1 by n is equal to 1 by n into delta QV divided by delta T, which is equal to Cv. Okay, so all these relations are very important for the exam. All right, everyone. If you have any doubt, please ask. Okay, let's see. Here Cv is the molar specific heat at constant volume, which defines how much heat is required to raise the temperature of 1 mole of gas by 1 degree Celsius or 1 Kelvin. Clear? So when volume is constant, uh, here m is the molar mass and m is the given mass of the gas. Molar heat at constant pressure. So the specific heat of a gas at constant pressure means the quantity of heat required to raise the temperature of your one unit mass by uh, mass of gas by 1 Kelvin when the pressure of the gas is kept constant. It is mathematically written as Cp equal to delta Qp divided by m into delta T. Okay, or here delta Qp is the heat supplied at constant pressure and m is the mass of the gas and delta T is the change in temperature. So now if we talk about 1 mole of gas, then we define molar specific heat. Mass is denoted by m. So mCp equal to m into delta Q p divided by m into delta T, which is equal to 1 by n into delta Qp divided by T is equal to Cp. Okay, where Cp equal to delta Qp divided by n into delta T is the molar specific heat capacity of a gas at constant pressure. An important point is that specific heat at constant pressure is always greater than the specific heat at constant volume. So meaning Cp is greater than Cv. So the reason for this is that at constant pressure the gas is also expands, in which extra energy is used for work, and therefore more heat is required in the case of constant pressure. So Cp and Cv are related to each other according to relation. We can say Cp minus Cb equal to R by M. Alright. So our equation is called Mayer's relation, when where R is the gas constant, M is the molar mass of the gas. So we can write here uh, Cp minus Cv equal to R. This means that for 1 mole of gas, the difference between the specific heat at constant pressure and the volume is always equal to R. Specific heat in terms of degree of freedom. So for a gas at temperature T and having degree of freedom F and internal energy U equal to F by 2 nRT, and change in internal energy delta U equal to F by 2 N into delta T. This indicates how much the internal energy increases or decreases due to change in temperature. Alright, any doubt? So now that when we define specific heat at constant volume Cv as follows: Cv equal to 1 by 2 into Fr. So whereas the specific heat at constant pressure Cp is Cp equal to F by 2 plus R into R. Here the extra one that is being added to F by 2 means that at constant pressure the gas not only requires heat to increase its internal energy, but also requires extra heat to the work done on the surroundings when gas expands. Now the ratio of both specific heat, which is called gamma, gamma equal to Cp upon Cv, is equal to F by 2 plus 1 into R divided by F by 2 into R, which is equal to 1 plus 2 by F. This means that gamma directly depends on the degree of freedom F. When F is high, gamma is low, and when F is low, gamma is high. Okay? So these relations are very important for understanding thermodynamics and the behavior of gases, specifically in the heat capacities of the gases and adiabatic processes. Next is mean free path. So when a gas molecules move in space, they repeatedly collide with each other. So, okay, so the distance a molecule travels between two successive collisions is called free path, and that is the distance covered between one collision and the very next collision that occurs immediately after it is called the free path. The formula is mean free path equal to total distance covered divided by number of collisions. And if we talk about the mathematically, so we can say lambda equal to 1 upon root 2 pi d square into n. Okay, next is Avogadro's number. So Avogadro's number is the number that indicates how many particles, atoms, molecules or ions are present in 1 mole of any substance, denoted by Na, or the value of Na is equal to 6.022 into 10 raised to the power 23, irrespective of the nature of the particles. Alright. Thank you for your attention. Now we will solve some practice questions based on these topics. So are you ready for the practice question, everyone? Okay, please wait 2 minutes. Now we will solve some practice question. Okay. Now we will solve some practice questions based on thermal properties of matter and thermodynamics. This is practice question part 3. This is our disclaimer. So here we will solve some practice questions based on thermal properties of matter and thermodynamics. So question is, a solid body of a constant heat capacity 1 joule per degree Celsius is being heated by keeping it in contact with reservoirs in two ways. First, sequentially keeping in contact with two reservoirs such that each reservoir supplies same amount of heat. Second, sequentially keeping in contact with 8 reservoirs such that each reservoir supplies same amount of heat. In both the cases, a body is brought from initial temperature 100 degrees Celsius to final temperature 200 degrees Celsius. Entropy change of body in two cases respectively is what? So here question asks, what will be the entropy change of the body in both cases? Okay, that is, what will be the entropy change in the case first case and the second case. So according to options, the entropy change for both will be different in each case, each option. Okay, so given options A, B, C, D, so which one is correct? Please solve this question, everyone. Please solve and tell me which one is correct. Okay, I will give you hint. Entropy is a state function. Okay, so using this hint, please solve this question. So the correct option is B. Okay, let's see the solution. So because entropy is a state function, so the change in entropy should be the same in both processes. Okay, so entropy is a state function and the state variable depends on the initial and final states. It does not depend on the path. As we can see in the PV indicator diagram, here two paths are given, path A and path B. Here our initial states is 1 and the final state is 2. Okay, so whether the process is occurs via path A or path B, entropy will only depend on the initial and final positions 1 and 2. In both cases we can see that the initial and final positions are the same, meaning in both cases the initial temperature is 100 degrees Celsius and the final temperature is 200 degrees Celsius. This means entropy will be the same in both cases. So option B will be correct because in this option the same value of entropy, which is log 2, is given for both the cases. Okay, clear? Next question. Consider a collection of a large number of particles, each with speed v. The direction of velocity is randomly distributed in the collection. What is the magnitude of relative velocity between pairs in the collection? So assume there is a collection of many particles. Okay, each particle has a speed v and the direction of velocity of these particles are randomly distributed, meaning the direction of each particle can be different. Now the question is, what will be the magnitude of the relative velocity between any one pair in this collection? If you understand this equation, then in any container there are many particles and all particles are moving randomly. Now we have the two stage of magnitude of the relative velocity between a pair. So the which one option is correct? Please solve this question everyone. You have some time. Please solve. Option A 2b by pi, option B v by pi, option C 8b by pi and option D 4b by pi. Which one is correct? Please solve. You have 2 minutes. Please solve. Which one is correct? Tell me the answer. VK, Varsha. Are you solving? Okay. Which one is correct? So correct option is D. Alright. Let's assume we have two particles with an angle theta between the directions of their velocities as shown in the figure. So let particle A and particle B be the two particles and VA and VA be the velocity of particle A and VB the velocity of the particle B. Okay. So the magnitudes of VA and VB are equal to V. Therefore, their directions are different. So given the angle between them is theta. So we need to calculate the magnitude of relative velocity. So the formula for relative velocity is V relative is equal to VV minus VA. So we need to calculate the magnitude of V relative. So its formula will be magnitude of V is equal to under root V square plus V square minus 2V square cos theta. Now let's solve this. V square plus V square becomes 2V square. So the magnitude of V relative equal to square root 2V square minus 2V square cos theta. Now factor out 2V square. So V relative equal to square root V square 1 minus cos theta. So simplifying this further, we get V relative equal to 2V sin theta by 2. Okay. So here we have used a trigonometric property which is 1 minus cos theta equal to 2 sin square theta by 2. So the finally we have obtained this formula for magnitude of relative velocity when the speed of both particles is v and the angle between their velocity directions is theta. Therefore the magnitude of relative velocity will always be 2v sin theta by 2. Alright. So the average relative velocity needs to be calculated for all pairs. So the formula for relative velocity is given as v relative equal to uh, we can say 2v sin theta by 2 which depends on the theta. To calculate the average relative velocity, we integrate this expression from 0 to 2 pi. Okay, so when we substitute the values, so it will be v relative equal to under root integration 0 to 2 pi v relative d theta divided by integration 0 to 2 pi d theta. Just put the values, you will be get integration 0 to 2 pi 2v sine theta by 2 into d theta divided by integration 0 to 2 pi d theta, which represents the average relative velocity. So this process is simple because we are taking the average of relative velocities for all the for all uh, velocities. Okay, so taking average of relative velocity for all angles 0 to 2 pi, which gives us the overall average relative speed. Now uh, the magnitude of relative velocity will be obtained after integrating, so it will be 2v into 2 into minus cos theta by 2 0 to 2 pi divided by 2 pi. So solving it, you will be get minus 2v divided by pi cos 180 minus cos 0 degree. So it will be minus 2v divided by pi into minus 1 in minus 1. So when we solve it, you will be get 4v divided by pi, which is greater than the velocity of an individual particle. And this is the final answer. Therefore, the correct option is B. Okay. Next question. An ideal gas, molar specific heat CV 5R by 2 is taken along these paths ACB, ADB and AB. P2 equal to 2 into P1, V2 equal to 2 into V1. Along path AV, P equal to KV, where K is a constant. The various parameters are shown in the figure. Match the column first with the corresponding options of column second and mark the correct option from the codes given below. So you have to match the column first and column second and find out the correct option. Please try to solve this question, everyone. After that, we will provide the solution of this question. Please solve. You have some time. Which one is correct? Please solve this question, everyone. Are you solving? So the correct option is D. Let's see the solution. First, we will calculate the work done along ACB. Okay, and we know that if we add the work done along AC, okay, so the work along PCB and we get the total work along the ACB path. Okay, So the work done along AC will be 0 because this is an isochoric process, meaning volume is constant. Therefore, in this process, work done is 0, and now we need to calculate the work done along path CV. Okay, so work done along path CV is equal to the area under the curve. So pressure is P2, and how much did the volume change? So V2 minus V1. So the work done is P2 into V2 minus V1, and this is the work done along the path CV. Now let's calculate this. The next step will be P2 minus P2 V2 minus P2 V1, and we are given P2 equal to 2P1 and V2 equal to 2V1. So here we have substituted the values of P2 and V2 in this step. So what did we get? 4P1 V1 minus 2P1 V1. Okay. So finally, what will remain? 2P1 V1, because we know that the ideal gas equation is PV equal to nRT. So PV equal to nRT, and for n equal to 1 mole, PV equal to RT. And for this equation, we can write PV1 equal to RT1. Okay, where R is the gas constant and T1 is the temperature at point A. And P1 and V1 are the corresponding pressure and volume. So the work done along path ACB will be 2 into RT1. Alright. Now we will calculate the work done along path ADB. For this we will add the work done along AD and the work done along DB. So work done along AD will be P into V2 minus V1, and work done along part DB is clearly 0 because along part DB the volume is constant. So solving this, we will obtain P1 V2 minus P1 V1. Since V2 equal to 2 times of V1, when we substitute this, we get 2 P1 V1 minus P1 V1. Finally, by solving this, the answer will be P1 V1, which is equal to RT1, because we know the ideal gas equation, which is PV equal to nRT. So we will replace P1 V1 equal with RT1. In this way, we have calculated the work done along path ADB. Alright. Now we have determined the change in internal energy along AB. Therefore, to calculate it along path AV, first we will calculate the internal energy along path AC. Okay, and then add the internal energy along path CV. So solving this, delta UAC will be CV into TC minus T1, and for delta UCB it will be CV T2 minus TC, because the formula for delta U is N, we can say N into CV, C final, T final minus T initial. Okay, and here we are considering 1 mole of gas. So solving this, and answer will be 5 by 5 R by 2 into T2 minus T1, because in this question the value of CV is given. So CV equal to 5 by 2, 5 R by 2 here. So for an ideal gas, P1 V1 divided by T1 is equal to P2 V2 divided by T2. Okay, so here we are using the ideal gas equation, because for 1 mole of gas, PV divided by T will be equal to R, which is a constant. Here P is the pressure, V is the volume, and T is the temperature. Now we need to find T2. So after solving T2, we will be 4T1. Now we will substitute the value of T2 into the formula for internal energy. So the change in internal energy along AB, which was asked in the question, will be 5R by 2 multiplied 4T1 minus T1. And solving this, we will give 15 RT1 divided by 2. So this is the change in internal energy along path AB. Okay. So internal energy depends only on the initial and final states. not on the path. So for the process along path BCA, in which the final state is A and initial state is B, the change in internal energy for BCA is equal to the negative of the internal energy along path AB. Therefore, the change in internal energy along path BCA will be minus 15 RT1 divided by 2. Okay. So based on this calculation part, so we can say the matching of column first with column second is as follows. So A matches with 4 and B matches with third and first matches and C matches with first. Okay, and similarly D matches with second. So keeping in this mind which option is correct, think about it. D is correct. All right. Next question. Diatomic molecules like hydrogen have energies due to both translational as well as rotational motion. So from the equation in the kinetic theory, PV equal to 2 by 3 E. PV equal to 2 by 3 into E. E is what? So here uh, there is a 4 options. You have to find out the which one is correct. Please solve this question, everyone. Option A, the total energy per unit volume. Option B, only the translational part of energy because rotation energy is very small compared to the translation energy. Option C, only the translation part of the energy because during collisions with the wall, pressure related to the change in linear momentum. And option D, the translational part of the energy because rotation energy of molecule can be of either sign and its average overall the molecules is 0. Okay. Please try to solve this question, everyone. You have some time. So the correct option is C. In the relation PV equal to 2 by 3 into E, E represents only translational energy of molecule. So this is because when gas molecule collide with the walls, their linear momentum changes, which creates pressure. Only the translation energy of molecule is directly related to this pressure because the pressure is applied due to molecules collide with the walls and the transfer of momentum occurs through this. Therefore, if the total energy of the gas also includes rotational or vibration energy, it is not directly related to pressure. This relation between pressure and volume is valid only with translational kinetic energy. Therefore, only the translation part is considered in E. Okay. Next question. So this is a big question. So read carefully, everyone. An ideal gas, ideal monatomic gas is confined in a cylinder by a spring-loaded piston of the cross section 8 into 10 raised to the power minus 3 meter square. Initially, the gas is at 300 Kelvin and occupies a volume of 2.4 into 10 raised to the power minus 3 meter cube, and the spring is in a relaxed state. The gas is heated by a smaller heater coil H. The force constant of the spring is 8000 Newton per meter, okay, and the atmospheric pressure is 1 into 10 raised to the power 5 Pascal. The cylinder and piston are thermally insulated. The piston and spring are massless, and there is a no friction between the piston and cylinder. There is a no heat loss through heater coil wire, and the thermal capacity of the heater coil is negligible. With all the above assumption, if the gas is heated by the heater until the piston moves out slowly by 0.1 meter, then the final temperature is what? So here you have to find out the final temperature. Given options: option A 400 Kelvin, option B 800 Kelvin, option C 1200 Kelvin, and option D 300 Kelvin. So which option is correct? Please try to solve this question. So correct option is B. Okay, let's see the solution. So this is our case. So now you can see in the figure that there is a confined cylinder. There is a spring loaded piston. The initial temperature of the gas 300 Kelvin. The volume occupied by the gas is 2.4 into 10 raised to the power minus 3 meter cube, and the spring is in its relaxed state, meaning the spring is currently not under any tension or compression. The gas is being heated by a smaller heater coil H, and the force constant of the spring is given as 8000 Newton per meter square. Okay. So if the gas is heated by the heater such that piston slowly moves outward by 0.1, then we need to find what is the final temperature of the gas will be. So let's see first the quantities which is already given. V1 equal to 2.4 into 10 raised to the power minus 3 meter cube, and P1 equal to P naught is equal to 10 raised to the power 5 Newton per meter square. Here T1 equal to 300 Kelvin, and if the piston's area of cross section is A and it moves a distance x, then the increase in the gas volume will be Ax, and it is given that the force constant of spring is given. For a spring force F equal to Kx, we have studied this before, and pressure equals to force upon area. Okay, so we can say F equal to Kx, so F by A equal to Kx by A. So if we substitute F equal to Kx into the pressure formula, pressure will become Kx by A. Alright. So if we assume that the initial volume is V1 and it has made an increment of Ax volume, then the final volume V2 will be equal to V1 plus Ax. And the initial volume V1 is 2.4 into 10 to the power minus 3 meter cube. And what is the increment? Ax. So all the given values we will put in this formula. So just substitute the values and solve it. you will be get V2 equal to 3.2 into 10 raised to the power minus 3 meter cube. All right, and P2 equal to P naught plus kx by A. So the atmospheric pressure is P naught, 10 to the power 5 Newton per meter square, and the pressure due to a spring whose formula is kx divided by area. So substituting all the given values, 10 to the power 5 plus 800 times 0.1 divided by 8 into 10 to the power minus 3. Solving these terms, we will get to P2 which is 2 into 10 raised to power 5 Pascal. So we will now use the ideal gas equation here. So the ideal gas equation is PV equal to nRT. Here R is a constant, so PV equal to PV divided by T will become to a constant because the number of moles N is also constant for the same gas. So P1 V1 upon T1 equal to P2 V2 divided by T2. So here uh, when we substitute the values, you will be get T2. So T2 equal to 800 Kelvin. This was asked in this question. So the correct option will be option B. Okay. Any doubt here? So the final answer is 800 Kelvin. When you solving this numerically, you will be get 800 Kelvin. Okay, everyone. Any doubt here? Yes or no? Tell me in the chat box. Okay. Thank you for your attention. That's all for the today. In the next lecture, we will start heat transfer. Okay. Thank you for your attention. Thank you.